So thanks, Diego. Thanks, Megan, for the invitation. Yeah, actually, I received an email that was a year ago, I think, from Diego and Megan. They asked me to talk about constraints, and I gladly accepted the invitation. So the goal is to talk about, yeah, as Diego said, and as you can see there, about database constraints. So my goal is to just introduce the very basics about constraints and the main technical tools that one should use to reason about database constraints. So for those who are familiar with these things, don't expect fancy stuff. For those who are not, I hope that this lecture will help you to get the very basics about this topic. Now, a couple of remarks. So these are, I will say, two good references for the material that I'm going to cover. The first one is the standard textbook about database theory, which goes back in the 90s, 1995, if I'm not mistaken, by, I mean, you all know the authors. Now, the second one is something that we are trying to pull together, but it takes a bit of time, unfortunately. So we were hoping that we will finish that book, I mean, before COVID. This didn't happen. COVID didn't help, of course, and we are still trying to write that book. But there is a preliminary draft available. Of course, it's not the whole book there. Is, I mean, some parts of the book, which we continuously update. So you can get it from this GitHub link. And why I'm mentioning that, because most of the material that I'm going to cover today, I mean, you will find them in this draft of the book, right? And therefore, I decided to skip a lot of technical proofs and low-level details, which I thought is not that interesting, since you can find them in the draft, and focus on the more high-level picture. I mean, apart from the definitions, some intuition behind the technical results, and anyway, the tools to understand what are the main tools and how one can use them. And for the low-level proofs, I will refer to this book, the draft of the book. It's not a book yet. Okay, and let's get started then. So here I'm just trying to summarize in a picture what we usually do in databases. So we have a collection of data structured in some way, right? And we have users posing queries over this data in order to get some answer, right? So this is usually what we do in databases. And of course, this is structured in some way. We need to make it a bit more precise. And usually we have a data model which tells us how the data is structured, right? So it's a mathematical abstraction for structuring the data, independent from the physical implementation. This is what the data model does for us. So we structure this data according to the underlying data model. And here I will concentrate on the relational model. Of course, the relational model, as we all know, is not the only one. There are several other data models out there. Actually, the next lecture today by Pablo, if I'm not mistaken, will talk about a different kind of data model. I mean, he will talk about graph data, right? The way of structuring our data as graphs. So here we are going to talk about the relational model. Now, a few words about this relational model. So this goes back in the 70s. So before the 70s, we had several ad hoc, I would say, data models, which were very difficult to work with. And why is that? Because they were very close to the physical implementation. And then it was this revolutionary idea by Cott, right, who said, okay, let's store data as relations or tables, right? And then let's query these relations using a declarative language, which is based on logic, right? And we have also the procedural analog, right, algebra, which allows us to execute queries procedurally, right? So that was the revolutionary idea by Cott. And although nowadays we think it's a trivial thing, that was quite important back then, and this secured actually the Turing Award to Cott, as we all know. So that was indeed a revolutionary idea. So again, we store data as relations, and we can use logic as a declarative language to query this. And we have also algebra, which is the procedural counterpart, right? So the user writes down the query as a logical formula, and the system can convert that into an algebra query, and then do all the magic that a database system does. All right, so a relational database, then, just to make it a bit more precise, usually comes, as we all know, with a database schema, which is a finite set of relation names. together with their attribute names, right? So here we have two relation names. It's flight and airport. And flight comes with three attributes: origin, destination, and airline, with their types, right? These are strings. And we have also the airport relation name with two attributes: code and string, and sorry, city, again, of string type. And together with this database schema, we have a database instance, which is essentially our data conforming to the schema. So here, as you can see, we have some tables under the relation name flight. So we have, I don't know, from Vienna, you can fly to London Heathrow, and this is operated by British Airways, and so on and so forth. And here we have the instance of this relation name, which says that Vienna is an airport based in, VIE is the code of an airport based in Vienna, LHR is based in London, it's London Heathrow, and so on and so forth, right? It's as simple as that. I'm pretty sure that we all know these things. And essentially now, if we can see these relation names as the header of a table, if we combine these two things, what we get are tables, right? And a relational database then is a finite set of such finite tables. That's it, as simple as that, right? Now, a couple of remarks here. So whenever we study relational databases from a foundational point of view, usually we ignore these attribute types, right? And we assume that all the data elements are coming from a countable infinite set that I denote here by const. So this is a countable infinite set of constant values. So all the data elements that you see are coming from this const set, right? So we usually do that to simplify things. I mean, all the results that I'm going to present, they are not affected by this. And actually, this brings the whole setting closer to mathematical logic, right? And that's why we do that. And also, from now on, I will see a relational database as, apart from seeing this as a finite set of tables, as the ones that we see on the slide, we can also think of a relational database as a finite set of relational atoms of this form, right? So from now on, whenever I say a database, I actually mean a set of tables like that without considering the attribute, or a finite set of relational atoms of this form. So as you can see, each table here can be very naturally translated into a set of relational atoms, right? So the four tables in this flight relation can be converted into these four relational atoms, and the airport table can be converted into this set of relational atoms, right? So a database then for us is a finite set of tables by ignoring these attribute types. I will keep using this table representation on the slide because it's nice and convenient, but I will go between this representation and the representation that you see on the slide here as a finite set of relational atoms. Okay, is that clear? I think it's pretty clear. Great. So that's a relational database, as simple as that. No more, no less. Now, once we have this notion in place, the notion of database in place, what we want to do is to query this data. And let's see a very simple example. Although querying relational databases is not our main concern in this lecture, but let's see a simple example. So imagine that we want to list the airlines that fly directly from London to Glasgow. We can very easily express this query using this first order query, which even if you are not familiar with first order queries, I guess you can easily understand what is going on here. So we are asking for an airport X, which is based in U, and we want U to be London, right? So this London is a constant value, which is coming from this countable infinite set const that I mentioned before. So we are looking for an airport which is based in London, and an airport Y which is based in V, and V should be Glasgow. And then we want a direct flight from the airport X to the airport Y operated by Z, right? And as you can see here, Z is my output variable. And actually the value that we are going to assign to Z, it will be the answer to our query, right? This is how you should treat such a first order query. All right, so this is how we can express this very simple query using a first order query. And now what will be the answer? Can someone say something? So what do you expect to be the answer here now? Can someone say something? Just shout. It should be, so we have a witness, one may say, for X, which is what is LGW, and U is London, right? So we have a witness for X that satisfies the relational atom. We have also a witness for Y, which is GLA, right? And B is Glasgow, fine. So we have a witness for this relational atom. And indeed, we have a flight from LGW to GLA, so from London Gatwick to GLA to Glasgow, operated by U2. And then one may say, okay, great, U2 should be an answer to this query. Okay. Now, my question to you is, are you happy with this answer? Can someone say something? Let's try to make it a bit more interesting instead of just standing here and talk for 3 hours. So are you happy with this U2? I mean, just looking your data there. Are you happy with U2, please? Very nice. So actually, just to repeat, because maybe you haven't heard. So here we are saying that what we just heard is that we have two actually airports with the same code there. LGW, okay, the first one is based in London, the other one is based in Larnaca, right, which is a city in Cyprus. And therefore, we are not entirely sure from this data that indeed LGW is an airport based in London, right? And therefore, can we trust this answer? One may say, no, you should not trust this answer. We are not entirely sure that U2 is indeed, we are not entirely sure that U2 is indeed the answer to our query, right? And the reason is precisely that, what we just heard. So here we need a way somehow to specify that the code of an airport uniquely determines the city, okay? So we need to find a certain way to specify that. So we need to specify this semantic property and accept only databases that satisfy this semantic property as valid databases, right? And then posing queries on such valid databases, right? Now, how we can do that? This is precisely what integrity constraints allow us to do, right? So, as I said, integrity constraints allow us to specify semantic properties that should be satisfied by every database instance of a certain schema, right? And we only accept this kind of database instances as valid instances, right? And we want to query only those instances. Of course, this is not always the case in real life scenarios to keep our database instances consistent with our constraints. And of course, there we need to find other more refined ways of querying inconsistent data, right? And this, I think, will be the subject of a lecture on Thursday, Wednesday by Jeff, right? So there, if we have an inconsistent, so even if we pose this restriction that the code attribute uniquely determines the city, nobody guarantees that always our database will be consistent. We don't want to scrub our data because this is the last thing that we want to do. But then we can't just evaluate the query as I just did and say U2 is an answer. There we need more refined ways. And this is what we are going to hear on Wednesday by Jeff. But now, here I'm just saying that let's assume that always our database is consistent with the given set of constraints which specify these semantic properties. And now we can just evaluate your query over this database in the standard way and then trust your answer. Right? So integrity constraints then help in the development of transparent and usable database schemas. And also, as we shall see later in the lecture, they play a crucial role in optimizing queries. Okay? So that's why we care about integrity constraints and we want to study them, right? There are several classes of constraints out there. Actually, in the 70s or 80s, people went mad with this topic and they were introducing classes of constraints every month. So you will find several classes of constraints out there, but I will say the constraints that we most commonly use in real life systems are what we call functional and inclusion dependencies. And these are the kind of constraints that I would like to discuss with you today, right? So as I said, there are several other classes of constraints that you can find out there, but today we are going to focus on these two important classes, right? Which, as I said, are constraints that allows us to specify semantic properties about our data. Okay, so let's try to see what are these functional and inclusion dependencies. So are there any questions, by the way, so far? So whenever you have a question, just raise your hand, just ask, okay? All right, so what are functional and inclusion dependencies? So let's see this by a very simple example first, and then I'm going to introduce formally the syntax and the semantics of these constraints, right? Now, let's consider this very simple schema. We have just two binary relations. By binary, I mean relations with just two attributes. We have the person with ID and name, and the profession with the person ID and the name of the profession. And here we would like to say that the ID of a person uniquely determines that person, and this can be easily expressed via a functional dependency, which has this syntax. So here we are saying that the first attribute of the relation person functionally determines the second attribute. Here I could use actually the name of the attribute. I could use PID uniquely determines name, but it's just more convenient for me at least to use, which means that the order in which these attributes appear matters, right? So the first attribute is PID, the second attribute is name. And I'm simply saying here that the first attribute, which is person ID, uniquely determines the name of the person, okay? We would also like to say that whatever value we see in the person ID attribute in this profession relation should be a person ID. So we don't want to see something else in the first attribute, right? We don't want to see in the first attribute profession, I don't know, Andreas, right? This can be easily expressed using an inclusion dependency, which has this form. So here we are simply saying that all the values that you can read it in this way. The set of values that appear in the first attribute of the profession relation should be a subset of the set of values that appear in the first attribute of person, right? Which means that there is no way to have a value in the first attribute of to store a value in the first attribute of this profession relation, which is not the ID of a person, right? And a key difference between these two kind of constraints is that with inclusion dependencies, we can somehow say things that involve more than one relations, right? With functional dependencies, we can only talk about one relation name, here person. With inclusion dependencies, we can say things that involve more than one relation, right? Okay, so these are, by a very simple example, the kind of constraints that we're going to work with. And as I said, these are the most commonly used constraints out there. So let's start with functional dependencies. Please, Jorge.
Is it true that there's no way to like create a functional dependency that does the same as the inclusion dependency?
How you're going to do that, which involves two relations?
Depend on the names in the columns. Maybe you can say something about that.
I'm not aware of. I don't know how to do that. We can discuss it offline. But look. Yeah, I don't see how you can do that. I don't see how you can express in general an inclusion dependency using a functional dependency. Otherwise, we wouldn't have this as separate.
Yeah, these are extremely expressed with boundaries.
Yeah, you can express different things you can express things with inclusion dependencies, yet you cannot express with functional dependencies and vice versa, I would say.
Functional dependencies have the property that subsets are always consistent.
Yeah, for example, very good, very good. So if I give you a relation which satisfies a certain functional dependency, whatever subset of this relation you get will still satisfy the functional dependency. This is not the case with inclusion dependencies. So this is already a good argument that it says precisely what I just said before. Okay, so let's see now what is the syntax and the semantics of these dependencies slowly, okay? So a functional dependency sigma. So from now on, I will use this Greek letter sigma. And also whenever you see blue on the slide, it means this refers to a constraint, right? So a functional dependency sigma over a certain schema is an expression of this form, where R is a relation name coming from the schema S, and X and Y are subsets of this set of numbers, right? From a subsets of the set 1 up to REDR. Now, what is REDR? Is the first time that you see this notation. REDR, it's essentially the number of attributes of the relation name R, right? So it's the number of attributes in there. It's the arity of our relation, right? And from now on, I will just use this simple notation. So X and Y then are subsets of 1 up to arity R, right? And that's it. So this is the syntax of a functional dependency. Now, to relate with things that you may know from your database course, so because you heard about key dependencies, maybe you heard about primary keys. Now, if the union of X and Y is the whole set 1 up to arity R, right? Then sigma is what we call a key dependency, which we usually denote in this way. In some textbooks, you will see this notation. So here, what I'm saying is that a key dependency, which I'm pretty sure you all heard in the past, it's a special case of a functional dependency, right? So it's a functional dependency with this additional property. And in addition, we know that if sigma is the only key, because we may have more than one keys for a relation, right? But if sigma is the only key of this relation R, then this sigma is called the primary key of the relation, right? So what I'm saying here is that key dependencies that I'm pretty sure you know, it's a special case of functional dependencies. Please.
Don't you also have to say key mean function is minimal? Otherwise, if you take X to be the intersection or Y to be the intersection.
Can you repeat? I'm not sure I understood. Can you repeat that?
For key, don't you have to say X is minimal?
What do you mean by minimal?
For instance, if both X and Y is equal to the set.
But you can say that. I mean, it's a valid key to say that, right?
But then there cannot be a primary key because there is always like more than one key.
Look, I mean, if you express just one key, which is the one that you just mentioned, right? I'm not sure I understand.
Yeah, I mean, you can always define several functional dependencies in that our keys have more than one. But if you just have one, then it's a primary key. If you just find one,
I don't understand the confusion, sorry.
The usual term of keys are sets of attributes. And
Yes.
We're talking about the dependencies being the key. Dependency key and the primary key, this is the notion of the dependency. It doesn't have a notion of the minimality. We talk about a set of attributes being a key, we talk about minimality. A is a key, then A, B, C is also a key because it includes A.
Okay.
But here the terminology is about the dependency.
All right, look, let's go on then, right? And we can, Floris is smiling there. You want to?
No, I think it's just like some of you have like assume that the left-hand side is
Okay.
number of attributes, so your key R is X is then assumed.
Okay, fine.
This whole system is like that.
Okay, perfect, fine. Okay, so this is the syntax of functional dependencies. I will not mention keys again, right? Just to be on the safe side. So we're going to talk about functional dependencies. I'm very surprised that these things are popping up, but it's perfectly fine. So this is the syntax of functional dependencies, okay? Now, here I'm just saying that what we have seen before, this one functionally determines two, it's nothing else than the key of the relation person, right? So we're just saying that the first attribute is the key. But I think it's pretty clear what we mean here. Now, what about the semantics? So, and the semantics can be defined in this way. So, a database instance, D, and from now on, whenever you see green, it refers to a database, right? So we have this color scheme here. So a database instance D of a certain schema satisfies an inclusion dependency of this form. And I will denote that from now on using this notation. Sorry, what I said? Sorry, functional dependency. So, and I will denote that using this notation from now on, D satisfies sigma, if the following holds. Whenever we have two R atoms of this form in D, and recall that the database for us is a set of relational atoms, right? So a table can be seen as a set of relational atoms. So whenever we have such two atoms in our database, then the following should hold. If we project these two tables, A1 up to AN and B1 up to BN over X, and what we get is the same. So if the projection of those tables over X coincides, then what we expect that their projection over Y should also coincide, right? So it's an if-then statement there. So if, and projection, I mean, this notation, I guess it's pretty clear what I mean. So if I give you this table and I say project over the first, second, and the fourth attribute, what I'm going to get is this table, right? I will get the table A, B, and D, right? This is what I mean by projection. So, and again, if the projection of those tables, A1 up to AN and B1 up to BN coincide if we project over X, then the same should hold if we project over Y. And that's it. It's as simple as that. Okay. And we further say that the database satisfies a set of constraints of functional dependencies, which I denote with this capital Greek letter sigma. So this satisfies this set, which is denoted in this way, if the database satisfies every functional dependency in this set of functional dependencies. Okay. So I use the same notation then to say that the database satisfies a single constraint, and the same to say that the database satisfies a set of functional dependencies, meaning that it satisfies every functional dependency in there, right? Now, if you see this statement, as I said before, it's like an if-then statement. If something holds, right, which is this equality, then something else should hold. And actually, this can be also easily expressed using logic, right? So if we go back to our person example, where we say that the first attribute should functionally determine the second, essentially we are saying that whenever we have two relational atoms, person relational atoms, that they agree on the first attribute, and as you can see there, I use the same variable x to precisely say that, right? And they have some other value y and z in their second attribute. So if this is the case, so if I have two atoms that they agree on the first attribute, then I expect y and z to be the same value, okay? So which means that the semantics of when a database satisfies a functional dependency can be easily expressed in this way. Or you can think of it in differently. Actually, one can express an inclusion, a functional dependency using logic in this way, right? So this is actually a special syntax that database people introduced, just a more convenient syntax, which doesn't involve variables and quantifiers and other logical operators. But in the end, this is nothing else than this first order sentence, okay? So it's just a logical sentence with a special syntax. Great. And let me just say, for those who maybe heard about that, so essentially, functional dependencies are nothing else than a special case of a more general class of constraints known as equality-generated dependencies, which are first-order sentences of this form. So an equality-generated dependency is a sentence of this form where phi of x is a conjunction of atoms. So one can express if some conjunction holds, then we expect some values to be the same, right? So this is what we call equality-generated dependencies. And every functional dependency, right, can be expressed as a set of equality-generating dependencies, right? But I will not say much about equality-generating dependencies, EGDs for short. I will just focus on functional dependencies. But I just wanted to make the connection for those that are somehow familiar with EGDs. All right. So any questions about the syntax and the semantics of functional dependencies? I think it's pretty simple, huh? What is going on? Great. Now let's go on with inclusion dependencies then, which is also pretty simple. So an inclusion dependency over a schema is an expression of this form now, right? Where R and P are relations coming from, are relation names coming from the schema S. And now all these I1 up to IK and J1 up to JK, these are non-empty lists of distinct integers. In the first case of I1 up to IK, these are integers coming from this set, from 1 up to the RED of the relation name R. And J1 up to JK, these are numbers coming from this set, from 1 up to the RED of P. Let me recall you that the RED of but with this notation, I just refer to the number of attributes in the relation name, right? And that's it. That's the syntax. Okay. So essentially, what such an inclusion dependency tells us is the following. Let's see this by a simple example, and then we will formalize the semantics. So essentially, this tells us the following. If I have a tuple in the relation R, right? Let's say A, B, C, then what I expect is to see a tuple in the relation P where in the first attribute of P, I should see the value that appears in the second attribute of the tuple in R. Right, so here, for example, I have this tuple where in the first attribute of P, I have B, which is the value coming from the second attribute of the tuple ABC in the relation R. And the same with the other numbers. So in the third attribute of P, I should have the value that appears in the first attribute of R, and that's why I have A there. Okay, but I don't care. The inclusion dependency doesn't tell me anything about the second attribute. There I can have whatever value. There is no constraint about the value of the second attribute of P. So which means, again, for each tuple that I see in the relation R, I should have a tuple in the relation P that satisfies the constraint that we just discussed. So in the second case here, CDE, since I have CDE in R, I should also have such a tuple in P, which again, let's do this exercise. Here I have D because D appears in the second position of R, and in the third position of P I have C because C appears in the first position of R. Is that clear? This is what inclusion dependencies allow us to do. And now, having this in mind, I think it's very easy to formalize the semantics. So given a database and an inclusion dependency of this form, we say that this database satisfies sigma. I use, again, the same notation to say that the database satisfies an inclusion dependency, right? It's the same notation that I used before for functional dependencies. If what? If for every atom of this form R, A1 up to AN that I have in the database D, there must be an atom P, B1, Bm in D, such that what? The projection, if I project the tuple A1 up to AN over this list of integers, this should coincide with the projection of the B1 up to Bm tuple over the J, the list of J1 up to Jk integers, right? That's precisely what we are saying. Are there any questions? Please. What do you mean by express now here?
I mean, I assume that there are constraints that are not expressed using,
Yes, actually, there are some model theoretic properties, right? That you, okay, for example, of course, these things have been studied in the ontological setting, but the rules that we use there are similar to inclusion dependencies. And there you have some model theoretic properties like if I have a database that satisfies a certain set of, let's say, inclusion dependencies, then this should be, for example, closed under direct products and some other locality properties and stuff, right? So we have such model theoretic characterizations. And for sure, from there, you can use this to prove that there are things that cannot be expressed as inclusion dependencies. For example, already, if I go to, okay, let me just, if we go to guarded TGDs, for example, which I'm pretty sure you know, right? We can prove, okay, guarded, just to answer this question, if you don't understand what I'm saying now, it's not a problem because it's not part of the lecture, but a guarded rule, it's essentially a generalization of inclusion dependencies, right? Where you can say a conjunction of atoms implies an atom. And in this conjunction of atoms, you need a guard. What is a guard? It's an atom that contains all the variables, right? So it's a generalization. So we can prove, for example, using these model theoretic characterizations that there are things that you can express with guarded rules that cannot be expressed using inclusion dependencies, for example, right? So we have these kind of things. I don't know if this answered the question, but Yes, that's precisely why I decided to concentrate on that, which I think it's a fair thing to say. I haven't seen anything else other than inclusion and functional dependencies, to be honest, out there. Maybe I'm wrong, but
I guess there's no result of the thing like inclusion dependencies are the inclusion dependency properties are all first order sentences closed under block. I don't think there is such a kind of characterization.
No, I'm not aware of that. What I'm aware of is this model theoretic characterization. So if I give you a set of databases, right, with a certain model theoretic characterizations, you know that, or how I can express, how I can say that, a set of databases satisfy the set of inclusion dependencies even only if these guys enjoy certain model theoretic properties. We have such kind of things. No, you cannot express transitive closure with, yeah. Yes, so you can use these model theoretic characterizations that I just mentioned to prove such kind of things, that the transitive closure property cannot be expressed using this kind of constraints. All right, so this is how we define the meaning of inclusion dependency. So when a database satisfies an inclusion dependency, and again, we say that the database satisfies a set of inclusion dependencies now, using again the same notation, if the database satisfies every single inclusion dependency in that set. Okay. Okay. Now, again, as we discussed for functional dependencies, also inclusion dependencies can be seen as first order sentences. And this is related to what I was discussing now. So if you think about it again, this is an if-then statement. So we are saying that if there is an atom of this form in the database, then there must be some atom of this form, PB1, BM, in the database with some property, right? So this can be nicely expressed using a first order sentence of this form. So let's go back to our example. This inclusion dependency can be expressed in this way. So whenever we see a tuple or a relational atom profession XY in the database, then in this database, we expect to see also an atom of this form. As you can see here, the variable X is propagated, right? So it means that the same value should appear there. But now concerning the second attribute, there, as we discussed, the inclusion dependency doesn't pose any constraint. So when we translate to logic, there we are just going to say there exists some value. We don't care what is this value. We're going to use this existentially quantified value. So every inclusion dependency then can be written equivalently as a first order sentence of this form, where in the left and the right hand side of this implication, we have just one atom, right? So which means that one can think of inclusion dependencies as logical sentences of this form. So again, as I said, for functional dependencies, this syntax, it's something that database people introduced for representing first order implications of this form. So I think there was a question. No. Here I'm just saying, I give you, right? You are given a set of functional or inclusion dependencies, right? And then I'm not posing any minimality condition there. I'm just saying you are given, and here I'm just defining when a database satisfies this set, right? And I'm just saying that this set is satisfied if every single constraint in there is satisfied. So I'm not posing any minimality condition here or no. I'm just saying, given such a set, No, I'm not care about the redundancies here. I'm not getting into these kind of things, right? Okay, just referring to a set of functional or inclusion dependencies. Let's not complicate things, right? I'm just referring to a set of constraints. Okay. All right, so again, these are essentially logical formulas of this form, which are a special case now of what we call tuple generic dependencies, which are essentially formulas, sentences of this kind. So phi and psi are conjunction of atoms. So a tuple generic dependency allows us to say that if something holds in our database, so if a conjunction holds, then some other conjunction should hold, right? And an inclusion dependency precisely tells us that, allows us to express such a thing. The difference is that here in the left and the right-hand side, I don't have a conjunction of atoms, I have just one atom. So an inclusion dependency is essentially a tuple generic dependency where in the left and the right-hand side, the body and the head of this rule, we have just one atom, right? But one can express way more things with tuple generic dependencies, TGDs for short, but I will not get into these things. I will just stick to inclusion dependencies, right? So what we have seen so far, we have functional dependencies on the one hand, inclusion dependencies on the other hand, and actually these things can be generalized all the way up to equality generating dependencies and tuple generating dependencies, right? So one can see EGDs and TGDs as somehow a unifying framework for constraints. So actually, every kind of constraint that you can find out there, other than functional dependencies or inclusion dependencies, actually can be expressed as an EGD or a TGD. So equality and tuple generating dependencies should be understood as a unifying framework for integrity constraints, right? But in this lecture, as I said, I will not consider these expressive classes. I will just stick to functional and inclusion dependencies. Okay, that's the story. Okay, let me finish with this just to conclude that, and then I'll get your question. So just to make this point here clear that an inclusion dependency is a first order implication in the end, let's see also this example. Imagine that we have these two relation names. We have this inclusion dependency. This can be now easily expressed as this first order sentence, right? So as you can see here, we are saying what? The second variable here, which is y, will appear in the first position of P, and the first variable, which is x of R, will appear as the third attribute, right? So this now, and we don't care, we don't have any constraint about the second position there. That's why we use the existentially quantified variable. Some value will appear there, right? So this first order sentence expresses exactly the same thing as this inclusion dependency. So is it clear what I'm saying here? Great. Jorge.
Just the tuple generating dependency plus what's the name of
Equality.
both covers all the possible.
Look, as far as we know, yeah, all the constraints, classes of constraints that have been proposed, right? They can be embedded in this more general framework, right, in the end. So whatever is the syntax of these guys, in the end, they can be translated into rules, into constraints of this form.
It's not something that is proven.
Okay, now I can come up with a fancy class of constraints that doesn't fall in there. But all the meaningful classes of constraints that you can find in a textbook, right, in Abidebul's et al. Textbook, for example, they can be embedded in this more general framework.
Yeah,
okay.
My question is maybe I didn't understand, but the inclusion dependencies are equivalent to the tuple generating dependencies?
No, it's a special case. It's a special case. So what I just said is a tuple generating dependency is a sentence of V and C being a conjunction of atoms. Okay, I can have V and C's. I can have more than one atoms there in conjunction. An inclusion dependency now is just a special case of such a sentence where phi and psi are single relational atoms. And we can prove, of course, that with these kind of things, you can express more than inclusion dependency. Great. Okay. So these are the main classes of constraints that we are going to concentrate on, inclusion and functional dependencies. And now, since we know the syntax and the semantics of these guys, right, let's go on with some basic algorithmic tasks that we would like to, that are coming together with these constraints. So, and what I call basic tasks are what we see on the slide here. So the obvious one is, first of all, to be able to check whether a database is valid or consistent with respect to a set of constraints. So is it the case that the database satisfies a set of constraints? I would like to be able to check that. And also, a bit more interesting from a technical point of view at least, is whether we can discover new constraints from existing ones. So if I give you a set of constraints, right, is it possible from this set to discover new constraints that always will be satisfied, right? And we will make this precise in a while. And this brings us to these two tasks. what I call the satisfaction and the logical implication problems, right? So let's see what are these guys. Of course, each one, for each class of constraints, we can define the analogous problem, right? And here I define both, which are defined in exactly the same way. The only thing that it changes is the class of constraints. So the FD satisfaction problem is this decision problem here. So what do we get as an input is a database of a certain schema and a set sigma of functional dependencies over S, right? It's just a given set of functional dependencies. And the question now is whether the database satisfies sigma. That's it. And the same, I can define exactly the same problem for inclusion dependencies. Okay. So, and I think if I give you now 2 minutes or even less than 2 minutes, you will figure it out how to solve this problem easily, right? Just implement the semantics. You don't have to do much. In the case of functional dependencies, we can easily show that this is feasible in polynomial time. How? Just do the following. I mean, this is a very naive algorithm. One can, of course, improve it. But for understanding the complexity and show that this problem is in p time, one can just apply that, which, as I said, I just implement the semantics here. For every functional dependency in sigma, what do? We just check for every pair of atoms in the database whether this if-then statement holds. If for every 2 atoms, the projection over X agrees, but the projection over Y disagrees, then we fail, right? So if I go through that and I find a case where this fails, it means that there is some inclusion dependency that is not satisfied, and therefore the database doesn't satisfy the set of functional dependencies. Now, if I don't fail here, it means that I haven't managed to find such a witness, which says that for the fact that the database doesn't satisfy the set of functional dependencies, and then I can just return true, and that's it. So I just implemented the semantics here, nothing fancy. And I think it's clear that this is in polynomial time. Why? Because for each dependency, I have to consider quadratically many pairs, right? And for each such a pair, I just need to perform an easy check, which is this, the condition of the if statement, and that's it. So I think it's pretty easy to see that this can be done in polynomial time. Nothing fancy here. Okay, just implement the semantics. The same with inclusion dependencies, right? For every inclusion dependency, what do? For each atom R now, so as you can see here in the left-hand side of the inclusion dependency, we have the relation name R. So then we are going to check for each R atom in the database. If there is no P atom, right, where the projection according to the semantics is satisfied, then we fail. This is a witness that this functional dependency is not satisfied. And since we found the functional dependency that is not satisfied, then the database doesn't satisfy the whole set of, I said functional, inclusion dependencies. If we don't manage to find such a witness, then we are sure that the database satisfies all the inclusion dependencies and we are done. And again, this can be done in time. So for each inclusion dependency, we have to consider polynomially many atoms. There are atoms, and there we have to, for each such atom, we have to perform an easy check, right? So as I said, this is a very naive way of implementing that, but even this naive way shows that this can be done in polynomial time. One can do a bit more clever stuff here. But technically speaking, there is nothing interesting going on here apart from just implementing the semantics, okay, of these 2 classes. Now, things are getting a bit more interesting when it comes to the implication problem. So which is actually the problem related to the second task that I mentioned before of discovering new constraints, right, from existing ones. Let's see what is that. So let's try to define first when a set of constraints implies a single constraint. So given a set of sigma of constraints over a certain schema, we are saying that this set implies a single constraint, right, which I will denote in this way. So the set sigma, capital sigma, satisfies the single constraint if for every database instance D, whenever D satisfies the whole set, sigma, then this database satisfies also the individual constraint. So we say that sigma implies sigma if whenever all the databases that satisfy the set of constraints right, satisfy also the single constraint. Is that clear what I'm saying? And somehow this makes sense. I mean, this is, you can see now the connection with what I said before of discovering new constraints. So essentially, if I have this set of constraints, right, then from there I can find new, I can try at least to find new individual constraints that are implied by this set, right? And then I know that I can just add them in there without destroying anything, right? So is this notion of implication, logical implication, clear? Great. And having this in place, now we can define these decision problems, right, for each class that we are interested in. So in the case of functional dependence, actually they are defined in exactly the same way. The only thing that it changes is the class of constraints. So what do we get as an input is a set of functional dependencies in the first case and an individual functional dependency. And we are asking whether the functional dependency is implied by the set of functional dependencies, meaning precisely that, whether for every database D, if this database satisfies the set of constraints, then the database satisfies the single constraint, right? So we define FD implication in this way, and in exactly the same way, we can define the version of the problem by considering inclusion dependencies. Okay? And this is the problem, these are the problems that we would like to study now. But first, we have to be sure that we understand the problem. So is that clear? What is going on? Okay. Now, let's see how we do that. Of course, one may say just try to check for every database whether this is the case. Try to enumerate all the databases and then check if D satisfies sigma, whether D satisfies the individual sigma, right? But of course, this cannot be done, right? I cannot enumerate all the databases because there are infinitely many, right? So this naive way of doing it is not a decision procedure. We need something a bit more clever. So, and the strategy here is the following that we are going to follow for solving this problem. So we will try to characterize implication for functional dependencies in a certain way, right? Which will then help us to come up with an algorithm. Let's see how we can do that. So the first thing that I do here is, given a functional dependency of the usual form, I define this set, which I denote by violate sigma. So, okay, let me introduce the set and then we will see what is this. So we define this set violate sigma, which collects two atoms, two R atoms, right? R is the relation over which the functional dependency is defined. So now all these x1 up to xn, y1 up to yn are variables, right? That are coming from some countable infinite set var. So recall that we have already seen the set const, which are constant values, right? Now here, imagine that we have another disjoint set, countable infinite set var, of variables. So whenever we need a variable, we can take it from there. So these are variables. Now, all these x1 up to xn, these are distinct variables, so I don't repeat any variable in there, and the same for y, right? So for each distinct ij, xi is different than xj, and yi is different than yj. And in addition, and this is the crucial bit, for each I, I'm saying that xi is the same as yi, so I use the same variable, if and only if I appears in the set X in my functional dependency. So essentially what I'm trying to do here is to define what I call here the prototypical set of atoms that violate sigma. So if I tell you construct the minimal set that you can construct that violates sigma, what are you going to do? You are going to collect two atoms and you are going to equate variables only. Which variables? Only the variables that appear at the positions in X. And all the rest will remain different, right? That's it. This is what I call violate sigma. So essentially this violate sigma does no more and no less to build a set of atoms that violates this functional dependency, right? So you can think of this as the representative of all the sets of atoms that violate your functional dependency. Is as general as it can be. Okay, so for example, in this case, right, in this simple case, this set, it will be precisely what we see here. I only use the same variable at position 2. So x2 and x2, all the other variables are different. Right? Okay. Now, once we have this in place, our strategy will be the following. So we want to find a way to transform this, let's say, prototypical set that violates our functional dependency into some finite set of relational atoms, which I denote in this way. I just have this sub sigma there that satisfies sigma, such that this equivalence holds. So the set of functional dependencies implies the individual functional dependency if and only if this set now satisfies my individual functional dependency. So I want to characterize then the implication problem, which involves infinitely many databases, right, according to the definition. I want to characterize this by simply saying, look, to check that, it's enough to simply check whether a certain set of atoms, which I have to carefully construct, starting from this prototypical set, satisfies my individual functional dependency. That's the strategy. So I would like to characterize implication in such a way. Okay? And if I can do that, right, now, before saying that, you can think of this transformed set as a representative of all the database instances that satisfy sigma, right? You can think of it in this way. And I'll make this a bit more precise in a while. And now, if we manage to have such a way of transforming this violate sigma set into this new set, right? Then essentially we get an algorithm which does the following. Essentially, it constructs this set of atoms, right? In whatever way we can transform violate sigma into new this set, and then it simply checks for satisfaction. And we have already seen before that satisfaction is an easy check, right? So if this set of atoms satisfies sigma, then we are done, true. The implication holds, otherwise false. And this is indeed an algorithm because of this equivalence, providing that we have such a way of transforming violate sigma into this new set of atoms, right? So assuming that we have this way in place, then we get this is the algorithm, right? Okay, and the goal now is, or the point is how we transform this violate sigma into this new set. And we will see that in a while. Now, I think at this point, it's a good place to introduce the notion of homomorphism in order to explain a bit more precisely what I mean by this representative here, right? Because this is very sketchy, of course. And to formalize it, I need this notion. So I think at this point, it's a good point to introduce that. I'm pretty sure that most of you or all of you, you know that, but just to be sure that we are on the same page, let's try to introduce it properly. So a homomorphism essentially is a structure preserving function between two objects, right? So I want to map a certain object into some other object by preserving the structure. And by object, I mean this can be a set of atoms, can be even more complex objects. For us, essentially, we will be interested of homomorphism between atoms, right? Now, what is this guy? So a homomorphism from a set of atoms A to a set of atoms B, it's nothing else than a function from what these terms now is the first time that you see this notation. These terms A, it's essentially the set of variables and constants that appear in the set A, right? So if I collect all the variables and constants that appear in A, so it gives rise to this set. So essentially, this is a function from the terms in A to the terms in B, such that what? First of all, it preserves constants. So if T is a constant coming from this set const, then H should be the identity there, so it should map T to itself. And the idea here is what? If I have a constant in my database or in my query, I don't know, London, right? London is London, come with its meaning. And I don't want to map London to Glasgow or to some other constant value, right? So I need to preserve the meaning of the constant. And that's why H should be the identity over const. And the second condition is if I have an atom of this form in A, and I apply my homomorphism to this atom, then what I get should be an atom in B, right? So this atom now are HT1 up to HTK should be an atom in B, right? So this is the homomorphism, and this is what I mean by structure preserving function. Now, in addition, if this function maps the tuple U, so this bold-faced U, maybe you don't see very well that is bold-faced, but this is bold-faced, it means it's a tuple of variables. So if H now maps a certain tuple of variables U to a certain tuple of variables V, right? U is a tuple over the terms of A, and V is a tuple over the terms of B, of course. Then we say that there is a homomorphism from this pair to this pair, right? From A to B by mapping U to B, okay? And just an easy notation, a small notation. So from now on, I will write this, A goes to B, just to denote the fact that there exists a homomorphism from A to B. And I will write this just to say that there exists a homomorphism from A to B that maps U to B. Okay, that's it. So if we want to see graphically what the homomorphism means, it's essentially this. So if I have a set of atoms and I apply this function, which is from the terms in A to the terms in B, what I get, it will be a new set of atoms that lives somewhere in the set B. I don't have to touch all the atoms in B. But after applying H to A, what I get is a subset of B. Okay. Here is another example. So if I have this A set and this B set, so here is one homomorphism. So as you can see here, I map all the constants to themselves, and I map X to A and Y to B. So if I apply H1 now to A, you will see that I will produce this set of atoms. So X goes to A, Y goes to B, so this atom will be mapped there, and so on and so forth. You can easily verify that, right? So here is another homomorphism, right? If I decide now to map X to B and Y to C, after applying H2 to A, I get this set of atoms, right? So this tells us that we have more than one homomorphism from a certain set to another set, right? And that's it. This is the notion of homomorphism. It's as simple as that. Any questions about that? Okay, and now having this notion in place, we can come back to this representative, intuitive explanation that I was discussing before. And let's try to define this or explain this a bit more precisely. So recall that I said this violates sigma sigma. So this is actually what we get after transforming our prototypical set that violates sigma into some other set that satisfies the set of constraints. Now, this representative term, it means the following. It means that for whatever other database that satisfies sigma, right? And it's the image of our prototypical set. So in other words, in whatever way I can somehow specialize this prototypical set that violates sigma and get something that satisfies my set of constraints, right? So in whatever way I do that and get this database, this violates sigma sub sigma can be homomorphically embedded into the database D, right? So essentially, you can think of it as this violates sigma sub sigma as the most general set of atoms that satisfy sigma, right? And this is formalized values. So this representative set of atoms, it means precisely that. I hope this is clear what I'm describing. So again, the goal of this violates sigma sub sigma is first of all to satisfy sigma, of course, and for every database D such that my prototypical set that violates sigma can be mapped to it, and D satisfies sigma. So for every such database, we can find a homomorphism that maps this set to D. Okay. Okay. So this was to explain a bit better the notion of representative atom, and we will come back to this in a while once we see how this violates sigma sub sigma is generated, right? So this is the strategy, okay? This is what we want to achieve in order to solve the implication problem. So the big question now is how this transformation is done. That's the big question, okay? And this brings us to our main tool, which has been introduced decades ago precisely for tackling the implication problem, which is the chase procedure. So the chase procedure is precisely a way of transforming such a set of atoms into some other set that satisfies a set of constraints in the most general way. So let's see this via a simple example. It's a very simple algorithm, right? It's a very simple procedure. We just need to formally define it. So, but let's see this via an example first. And here I say FD chase just to clarify that I'm talking about the version of the chase that operates with functional dependencies, because later with inclusion dependencies, we'll have to do something different. So let's assume that we have this set of atoms and this set of functional dependencies. What the chase will do the following. So we start from the given set of atoms, and we see that the first functional dependency is violated. And why is that? Because we have the same variable in the second position, 2, but at the first position, we have a different variable. So this violates the functional dependency. And then the chase will do what? I guess you can imagine what the chase will do. What do I have to do now to satisfy this functional dependency? Just unify y1 and x1, and that's it. Make them the same. So in here, what I did is to replace y1 with x1. Of course, one may say, why you don't replace, I don't know, x1 with y1? I could do also that, right? You just need a way to equate these values. So here I decided to, and we will make this a bit more precise later, but here I decided to replace y1 with x1, and everything is fine concerning the first functional dependency. But now this second set that I produced violates the second functional dependency. Why? Because after replacing y1 with x1, I get the same value at the first position, but I have a different value at the third position. And the chase will go one step further and unify x3 with y3. And since we are building a set here, now I got the same atoms. And since we are building a set, in the end, the result will be Rx1, x2, x3 here. And that's it. Floris. Yeah, but then what I will build there, it will not be this representative set, no? No? Because, yeah, that's my answer. Because I will not be able to prove that if you do that. So your suggestion is why you don't destroy the equality there, right? But I don't think if you do that, you will be able to build this representative set, which can be homomorphically embedded into every other set that satisfies the set of constraints.
Sometimes you have a disjoint set of variables for every attribute.
Mm-hmm.
And every column has a disjoint set of variables. No reason to activate a variable from one column with a variable of another column. We only activate variables that are on the same column. If you have the one and it's still on the same line, you never interpolate.
So this is what the chase does very, very roughly, right? With functional dependencies. So the idea then again, we start from a set of atoms and we just do what the rules tells us, right? Until we get something by equating values, until we get something that satisfies the set of functional dependencies. Now, let's try to formalize this. Okay, it's very, very simple intuitively, but there are some details that we need to, anyway, we need to formalize it to be able to use it and be on the same page. Now, the very first thing that we need to define here is the notion of applicability. So essentially, when a functional dependency is applicable to a certain atom. So essentially, this will give rise to a single chase step. So let's see how we do that. So let's consider a finite set of atoms A. Here I say constant free. What constant free means, it means that I don't have constants in there. And I assume that for a good reason, which I will explain in a while, right? Of course, everything can be generalized to sets with constants, but let's assume constant free in order to get rid of some complications, which I will explain in a second. So let's assume that we have this set of atoms A and a functional dependency of the usual form. Now, what do we say here? We say that sigma is applicable to this set with this pair of tuples, U and V, where actually U and V are tuples in this R relation, right, in A, sorry. When sigma is applicable to A with this pair of tuples, it's obviously when, if the projection of these two tuples over X is the same, but the projection over Y is different, which means that U and V, the pair U and V, is a witness of the fact that alpha doesn't satisfy sigma, right? Because if I have such two atoms in the database with these two tuples, and this holds, it means that this is a witness of the fact that alpha violates sigma, right? Do you see that? Do you see what I'm saying? Okay, and here I'm saying that sigma is applicable to A with this witness, which witnesses the fact again that sigma does not, alpha does not satisfy sigma. And now, once I have this, I will go one step further and somehow apply this functional dependency over alpha with this witness, right? And what the application means is this unification of variables that we have seen in our example. And this unification is I formalize it via this function. So we define this function, which is parameterized by our witness UV, which is a function from the terms in the set A to the terms in the set A. Now here, since I assume constant free sets, essentially these are sets of variables, right? So we define, so this function is from the variables in A to the variables in A, such that what? For each such variable in A, this function will tell us what to do with this variable W. Are we going to replace it or are we going to leave it there? So, and let's see what this function says. So this function tells us that if W is one of the VIs in there, which means that it's a variable in a conflict, and UI, so VI is in a conflict with UI, but now UI it comes before VI in the lexicographically speaking, right? So this is what I mean by this symbol. UI comes before VI according to the lexicographic order, right? Now I will say what that means, but if this is the case, it means that we give priority to UI. So we are going to replace VI with UI. Now, if W, now in case that VI comes before UI, then we give priority to VI and we are going to replace UI with VI. And if W is not in these tables, right, it's not a variable in a conflict, so it stays there. Now, what is this lexicographic business there, this weird thing? This is just a mechanism, nothing fancy. It's just a mechanism which tells us which variable to replace with what. One can come up with something else, right? We just need a mechanism which deterministically tells us, look, if I have two variables in a conflict and I need to replace one with the other, just fix the way that you do this replacement. And here I decided to use this lexicographic order. So if UI comes before VI, just keep UI and replace VI with UI. And that's it. One can come up with something else. It's just a mechanism that allows us to fix the way that we replace variables whenever we have to, right? I hope this is clear. And once we have this function in place, then I think the result of applying sigma to alpha with this witness UV is clear. What is this thing? It's essentially the set that we obtain after applying this function to the set A. So after applying this function to the set A, which means I will unify some variables, I will get a new set of atoms A prime. And now this set of atoms A prime by construction will satisfy sigma, right? And this is actually a single chase step, which from now on I will denote in this way. So this notation here tells us that A prime is obtained from the set A by applying sigma to A with this witness, U and B, right? So this denotes a single chase step. So if we come back to our example, you will see now, you can see precisely the chase steps that we applied. So the first chase step, here we say that the first functional dependency is applicable to this set A with this witness, U and V. U, the second is V. And the same here, right? So with this strange notation, which is not that strange anyway, I just denote a single chase step. Is that clear? And now, since I have the notion of chase step in place, I can now go on and formalize the idea of starting from the given set and apply chase steps one after the other and keep doing that until I get something that satisfies the set of constraints. So this is formalized by the notion of chase sequence. So let's start with finite sequences. So a finite chase sequence of A under sigma is essentially a finite sequence of atoms, A0, A1 up to AN, where A0 is the given set A, is my first set, is the set that I start from. And now the second bullet simply says that for every two consecutive sets in there, right, A plus 1 is obtained from AI via a chase step, right? So for each I, there exists some functional dependency sigma, and atoms are U, are V in AI, such that AI plus 1 is obtained from AI after applying sigma to AI via this witness. So this is simply the formal way to say that each two consecutive or AI plus 1 in this sequence is obtained from AI via a valid chase step. And the last bullet here simply tells us that there is nothing else to do. So there is no applicable functional dependency on where? On AN, right? So for every functional dependency in there, and for every two atoms RU and RV, sigma is not applicable to AN with this witness UV. So in other words, there is nothing to do. So AN essentially satisfies sigma, and we are done. So this is the notion of chase sequence. Of course, at this point in our development, there is no reason to say that sequences are always finite, right? So one should go on and talk about also infinite sequences, which is defined in exactly the same way, right? It's an infinite sequence of atoms starting from A, and AI plus 1 is obtained from AI via a valid chase step, but we are missing the last bullet here, right? Because there is no last instance, or sorry, last set of atoms which satisfies sigma. Here we are simply saying that at each step there is something else to apply, and you may go on forever, right? So this is the way to define the notion of sequence, right? And the last bit that I would like to introduce before going to the key properties of the chase for functional dependencies is the following. It's actually the notion of chase homomorphism, which allows us to keep track of how variables are modified, right? So if I start from the very first set, the given set, I may replace, for example, X with Y, right? And then at the subsequent step, Y may replace with Z, and then Z with W, and so on and so forth. So I would like to keep track that eventually the variable X in the first set became the variable W in the last set. So I would like to keep track of how a variable is affected, right? And this is done via this notion of chase homomorphism, which can be defined very, very easily, right? Consider a finite sequence, finite chase sequence, which is a finite sequence of sets of atoms, such that each AI is obtained from, sorry, AI plus 1 is obtained from AI via some, the application of a functional dependency with a certain witness. And then to define this chase homomorphism, we simply need, which I denote by HS, we simply need to call all the functions that we have used at each single step. So recall that this is the function that we defined here, right? Which tells us how variables are replaced with other variables, right? And if I just compose all these functions, right, this will give me the notion, what I call the chase homomorphism, which tells us that a certain variable in the original set, what value this variable has now at the last set, right? And I guess it's easy to see now that if I apply this chase homomorphism on A0, which is actually A0 and A is my starting set, what I get as a result, it will be the last set of atoms in this sequence, right? And one could define the notion of chase homomorphism for infinite sequences, which can be done in the same way, but let's not get into that. Anyway, we are not going to need it, as we will discuss in a second, right? For infinite sequences, but we will need it for finite sequences for sure. So is it clear what is this chase homomorphism? So again, intuitively, it simply keeps track of how a variable is, its value is affected during the chase procedure. And now so that's it. This is the chase. It's a very simple procedure, iterative procedure that does what we discussed. Now, there are some things that we have to clarify here, because one may say, first of all, are there indeed infinite sequences? And as you can see from the first bullet, one can see easily that actually all the sequences are finite. And why all the sequences are finite? I guess the argument is easy, you can see it. So at each step, the only thing that we do is to equate variables, right? We will never introduce a new variable, which means that after finitely many steps, in the worst case, what I will get there is a set of atoms with just one variable, which trivially satisfies every functional dependency, right? So after finitely many steps, we will stop. So there are no infinite chase sequences of a certain set under a set of functional dependencies. Please.
Can we maybe try to make a
Sorry?
Can we try to make a circle?
How you are going to make a self-loop? Because recall what the chase step does. At each step, you equate variables. At each step, you equate variables, but you cannot reverse that. So at the next step is not that you can now. Okay, two variables are different, and at a certain step, you may make two different variables the same. That's it. This is what the chase step does. You cannot revert this, and you cannot introduce new symbols, right? You only do that, which means that at some point in the worst case, you will end up with a set of atoms with just one variable in there, right? Which trivially satisfies every functional dependence. So I think this is already an argument which tells us that there are no infinite chase sequences, right?
That you necessarily lose one variable in every step.
Yes, because otherwise you are not applicable, and you just stop there. So in the very worst case, you will end up with a set with just one variable in there, which there is no way this set to violate the functional dependency, and you just stop there. Actually, as we will see in a while, essentially after polynomially many steps, how many such unifications you can have, polynomially many. Now, what about the chase sequences now? So we define the notion of chase sequence, but this is not unique, right? Depends on the order that we apply functional dependencies, right? I can decide to apply this functional dependency now, but in a different chase sequence, I can decide to postpone that and apply something else earlier, right? So the order in which we apply the functional dependencies give rise to different sequences. Okay. And then what? Which one is the good one? So all of them are good ones. Why? Because they always lead to the same result, right? So whatever two finite chase sequences we consider, right? In the end, their result, AN and BM in this case, there will be the same set of atoms. So no matter in which order we are applying the functional dependencies, we will always get the same set of atoms. That's what we are saying. Which this allows us to refer to the unique result of the chase of A under sigma, which from now on I will denote in this way. So no matter which chase sequence we consider, we will always get the same set of atoms. And this also allows us to refer to the unique chase homomorphism, right? Which I will denote in this way, H of A sigma. Another property is that the set of atoms that we build satisfies sigma by construction, right? So if there is a functional dependency there that is violated, right, it means there is still something else to do, right? It means that our chase sequence is not a valid chase sequence, right? So in the end, the result always satisfies sigma. So this is related to what we discussed before. I can construct this set of atoms in polynomial time because the argument that we use for the finiteness, essentially the same more or less applies for that, because how many unifications I can have. After polynomially many steps, I will unify everything with everything and end up with just one variable in my set of atoms. And here is the last crucial property. Actually, this is the key property which makes the chase a useful tool, which is this representative set of atoms that we were discussing before. So consider some set of atoms A prime, and assume that we can map A, which is our starting set, to A prime via homomorphism, and the tuple of variables U to B, and assume in addition that A prime satisfies sigma, right? So for every such set A prime, we can prove that the set of atoms that we build via the chase can be mapped to A prime. And the updated version of the table U after applying the chase homomorphism. So after I compute the new table, depending on how variables have been replaced during the chase, this will give me a new table, right? This new table can be mapped to B. Okay. So this is the key property, which essentially tells us that what the chase builds is this representative set of atoms that it's a representative for all the set of atoms that satisfy a given set of functional dependencies. I hope it's clear what this says. And as I said, although everything is useful here, this is the crucial property that makes the chase such a useful tool, right? Which appears naturally when we reason with constraints. All right. And now coming back to our goal, remember, the goal was to find a way to transform this prototypical set that violates a certain functional dependency to something else, right? That allows us to characterize implication. Now you can imagine how we are going to transform this guy via the chase. So what we can prove, which I will not prove, but what we can prove by exploiting these properties of the chase, especially the last one, is the following. Given a set of functional dependencies and an individual functional dependency sigma, the implication holds if and only if the chase of this violate sigma set under sigma satisfies the individual functional dependency sigma. And this heavily relies again on this property here that we discussed before. The proof can be found in this draft of the book that I mentioned. I was planning to discuss the proof, but to be honest, nothing very interesting is going on there. Once we have the chase in place with this property, then it's not a very difficult thing to prove that. But now this proposition immediately gives us an algorithm for implication, right? What is this algorithm? It simply says, look, compute the chase starting from this prototypical set that violates sigma. And once you construct that, check whether this set of atoms satisfies sigma. Now, how complex is to construct the chase? We have seen that before. In polynomial time, we can construct this set of atoms, right? We have also seen that checking whether a set of atoms satisfies a functional dependency is in polynomial time, right? Which means that in polynomial time, I construct this set of atoms via the chase, and then in polynomial time, check whether this set of atoms satisfies my functional dependency. And if this is the case, I say yes, the implication holds. Otherwise, the implication doesn't hold. And this allows us to conclude that the implication problem for functional dependencies is in polynomial time. Okay, which, as you have seen, heavily relies on this tool that we call the chase. So what we have seen so far, we have seen what are constraints and why they are useful. We have introduced the syntax and semantics of functional inclusion dependencies. And we have seen what are the main tasks that we are interested in, satisfaction and logical implication. We have also proved, which is straightforward by simply implementing the semantics, that the satisfaction problem for both classes is in polynomial time. Just implement the semantics. And we have seen that the implication problem for functional dependencies is in polynomial time by heavily exploiting this tool that we call the chase. Now, what about inclusion dependencies? This is what we are going to do next. Things are getting a bit more complicated there, but maybe it's a good point now for a break. Okay. So, yeah, please.
What about the constant? We always talk about constant free.
Can you?
Constant.
Yes. Okay. That's a very good point. I forgot about that. So maybe we can come back to this after the break, or maybe can I take 2 minutes to explain that? It's up to you. Okay, let's finish with that, to wrap up with that before we proceed with inclusion dependencies later. Okay, yeah, that's a good point, thank you. Right, now here I said that the set of atoms, we are considering constant free set of atoms, right? Now, the catch here is the following. As you can see, during this chase procedure, we have to replace values with variables, right? Now, if you have constants in there, you may arrive at a point where two constants are in a conflict, which means that you have to replace A with B or B with A, right? But now this is what we call the hard violation, right? Because A, the constant A has its meaning, the constant B has its meaning. London is London, Glasgow is Glasgow. I cannot equate London with Glasgow. So which means that if I have constants in there, I have to carefully treat this additional case, which is a bit annoying, right? Which and then say that actually the chase fails in this case, right? There is a failure. And then we have to carefully treat this case. It can be done, but this is actually the additional complication that I just wanted to get rid of by focusing on constant free sets of atoms, okay? But it can be done. In this draft of the book that I mentioned, you can nicely see how is treated this case, okay? But actually by getting rid of that is not that we lose the essence of the chase procedure. I mean, the key idea is what we have seen, the key properties is what we have seen, and the whole strategy for solving the implication problem is what we have seen here via the chase. So we don't lose anything by just getting rid of this case. Okay.
So if you unify a constant in the variable?
Now, this is possible. Yeah, thanks to Benny. Now, of course, you may arrive, if you have constants, you may arrive at a point where a variable and a constant are in a conflict. Of course, in this case, you give priority to the constant. So imagine that, sorry for going back and forth. So imagine that in the definition of this function, in case that you have a constant and a variable in a conflict, here you will give priority to the constant. So you will always assume that constants in this lexicographic order are before the variables, and you always give priority to a constant. If you have to replace a variable with a variable, we have seen how this is done. If you now arrive at the point where two constants are in a conflict, there you fail. The chase fails, and this is what we haven't seen carefully. But as I said, I think it's okay to get rid of it, just to keep things simple. Okay, so I think we can have a break now then. So this is what we have seen so far. Let me turn this on. Okay. All right, so this is what we have seen so far. Are there any questions, guys, up to this point before we get on? So as I said, the next step now is to understand the implication problem for inclusion dependencies. But before we go to that, are there any questions? I hope it's not too boring what is going on. Okay. Now, let's go then to the implication problem for inclusion dependencies. So the strategy that we are going to follow for that is the same. So as for functional dependencies. So given an inclusion dependency of this form, we are going to define this prototypical set again, which violates an inclusion dependency, and then try to convert that into a set that satisfies the inclusion dependencies and so on and so forth. We will see the details, but let's see what is this set now. As you can see now, this set is very, very simple. So if I tell you construct a set, the simplest set that you can think of, which violates an inclusion dependency, what will be that? It will be just one atom, right? With the relation R, which is in the left-hand side of the inclusion dependency, and a list of distinct a table of distinct variables there. So this is the simplest set of atoms that you can think of that violates this inclusion dependency, right? Because if I build that without repeating any variables, without nothing, then I expect some p atom, which I don't have in there, of course. So this is the simplest atom, the prototypical set of atoms that violates this inclusion dependency, right? So here is, again, a simple example. I think it's so simple, this notion, that we don't even need an example. So in this case, it will be just an R atom with 3 variables in there, x1, x2, x3, right? And the strategy now, again, will be the same. We want to find a way to transform this set into something else, guided into a finite, right? And I stress that, should be a finite set, guided by the set of inclusion dependencies such that this equivalence holds. So it's the same strategy as for functional dependencies, right? And one may think that if we find such a way to transform this violate sigma set into this new set of atoms, then we will easily get an algorithm as we did for functional dependencies. Things are a bit more complicated now compared to functional dependencies, and we will see why and how we're going to deal with that. So it's not that straightforward as in the case of functional dependencies. But let's start with our main tool. So what will be this main tool for transforming this set into something else? It will be, again, the chase procedure. But now we have to redefine it for inclusion dependencies, right? So the chase, then, whenever you hear chase, you should think of it as a family of algorithms, right? It's not just one algorithm. depending on the underlying class of constraints, you have the corresponding version of the chase. And also, even in the case of inclusion dependencies, there are several different ways of defining the chase, achieving, of course, the same thing in the end, right? So I'll try to discuss a bit these things, but let's see how the chase works. So let's start with an example, as usual. So we are given this set of atoms over the schema, right? R1, Rx1, X2, X3, and these two inclusion dependencies. Now, what the chase will do here, I guess what you can imagine what. So we start from this atom, and the first inclusion dependency is somehow violated, right? So because I have an R atom, but I don't have a P atom, so the chase will fire this guy, and it will add now an atom, right? A P atom. And as you can see here, because the constraint tells us that we need an atom such that in its first position, we have the same value as the value at the second position of R, the chase will just put there X2. And then Y1 and Y2 are two fresh variables, right? We don't know, the constraint doesn't tell us anything about this, as we discussed in the definition of the semantics. We just know that these two values exist there, so I just use two fresh variables, Y1 and Y2, that have not been, that are not in the current set, right? So, but now you see already a key difference between the chase procedure for functional dependencies and the chase for inclusion dependencies. Here now we start introducing new variables, and we start adding new atoms in the chase, something that we didn't have to do with functional dependencies. There we are just equating variables. Here now we have to start introducing new things in order to satisfy a constraint. Now, after adding this guy, the second inclusion dependency is triggered because I have this P atom, and the inclusion dependency tells me that I need also an atom where in the first position I have Y1 and in the second position X2, right? And this is precisely what the chase will do. It will add another atom by just changing the order of these two guys. This is what the inclusion dependency tells us. And Y3 is again a new variable that the chase will plug there because we have to put something there. We don't know what is this value, it's just a fresh value. And in this simple example, the chase will stop here because there is nothing else to do. Okay. And this is a set of atoms now, which satisfies starting from, so we converted this set of atoms into this set of atoms, and it's easy to see now that this set of atoms satisfies the given set of inclusion dependencies. Good. But now things can get a bit nasty here in the sense that there are simple cases like the one that you see on the slide where we have to keep adding stuff in the set of atoms forever in order to satisfy the inclusion dependency. So in other words, we may have to build an infinite set of atoms. And let's see, and these cause problems, of course. And we will see that later. So let's see why we have to build an infinite set of atoms. So if we start from this, the chase will say, okay, we have to introduce an atom where X2 appears in the first position and X3 in the third position, right? But after adding this atom, right, this atom will trigger again this inclusion dependency. We will have to apply again this inclusion dependency, right? And the variable in the first position there will be Y1, which appears in the second position, and the third variable will be the variable in the third position of this atom. So it's Y1, X3. But again now, this atom will trigger again the same inclusion dependency for exactly the same reason, and we are forced to add this new atom, and there is no way to stop. Please. Now, the point is, as we said, we need to build this representative. I think this is exactly the same question as Floris before for functional dependencies. The goal here is not just to build the set of atoms that satisfies the constraints, but should be this representative set of atoms, which can be homomorphically embedded into every other set that satisfies the constraints. So if you start doing that, I don't think that you can build this representative. So the chase keeps adding things in the way that we discuss in order to be able to prove that what you build is this representative set of atoms that can be homomorphically embedded into every other set that satisfies the constraints.
Range will also be, you know, it will also be possible to embed it in.
Is that true? Yeah, but don't forget your original set of atoms, right? Your original set of atoms should be there. So you may remove something from this set. So the message that, just a second, the message that I'm trying to convey now here is that the chase for inclusion dependencies has to introduce new values and add new atoms. And there are very simple settings like this one here, just one atom in the set alpha A and just one inclusion dependency that forces the chase to build an infinite set. Okay, let's keep this in mind, please.
Does that mean that there's no finite representation of
No, you can find the finite set. For example, RXXX, for example, it's an atom that satisfies your inclusion dependency, right? Or no, differently, forget it. You can, for example, I don't know, reuse something here, X2, X2, right? And this will satisfy your inclusion dependency. But this will not be this representative set of atoms that we are looking for. So the chase is trying to do no more and no less than what you need to satisfy the set of constraints. So here, for example, I can close the loop by just, no, what I said maybe is wrong. So, okay, for example, use here X2, for example, instead of Y1. Let me see how you can, okay, let's not get into that. What I'm trying to say is the following. There is a way to build a finite set of atoms, right, which contains A and satisfies the set of inclusion dependencies. I'm not saying that there is no such a thing, but this set of atoms is not the representative that we are looking for. So the chase keeps adding things, and whenever you need a new value, you just invent a new value, and you go on like that in order to be sure that you build this representative set of atoms.
Well, my question is the fact that the chase doesn't stop means that there's no finite representative of
Yes, that's what. No. The chase is not a complete procedure in this sense. So you may have a finite such representative, but the version of the chase that we are discussing here may not find it. But there is a more clever version of the chase, which always will find this finite representative if it exists, right? But we don't really need to get, for solving our problem, and usually the version of the chase that we use is this. We don't really need to get into this more sophisticated version of the chase. For those who are interested or know, I'm talking about the core chase, which if there exists a finite representative, this version of the chase will always find it. But of course, this is more complicated to define. It does other stuff than just adding atoms. Okay, so the answer to your question is yes, there may be such a finite representative, but this version of the chase will not find it, okay? Okay, so the message that I'm trying to convey, is, as I said, is that we may have to build infinite set of atoms. Okay, now let's define this formally. Now you got an idea what is this chase for inclusion dependencies. You already know that it may build infinite stuff. Now let's try to define it formally as we did for functional dependencies. So let's consider a finite set of atoms and an inclusion dependency. Let's try to define the applicability notion here. So we are saying that sigma is applicable to A with this table if such an atom R U1 up to UN belongs to A, right? And that's it. Now one may ask, but why you consider this U as a witness now for the violation of the constraint? Because maybe in A, we already have a P atom, right? That satisfies the constraint, despite the fact that RU1 UN is in A, maybe there is already a P atom in there that satisfies the constraint, right? But as you can see here, the applicability notion that I defined doesn't take this into account, okay? Now, the way that we define, depending on the way that we define the applicability, gives rise to different versions of the chase. The version that I'm defining here, it will eventually give rise to what we call the oblivious chase, which is actually the naive, let's say, version of the chase, which doesn't really check whether a constraint is really violated. It just fires rules as long as the left-hand side of this inclusion dependency is satisfied. As long as there is an atom with a relation R, the chase will say, okay, this is a good reason to fire this inclusion dependency. There is a bit more clever version of the chase, which we usually call the restricted. And this is actually what people consider the standard version, which the applicability condition there is a bit more clever in the sense that it really checks whether this guy is violated. Okay. Now here I decided to focus on the simple version for a good reason that I will discuss later. But have this in mind. Have this in mind. Depending on how you define this applicability condition gives rise to different versions of the chase. We have the oblivious. There is a version called semi-oblivious. There is a version called the restricted chase. All these versions of the chase differ on how this applicability condition is defined. Here, for the sake of simplicity, and because this version is good enough for our purposes, I decided to stick to the naive one, which again, it says sigma is applicable to you with this tuple only because such an atom belongs to A without caring if the inclusion dependency is already satisfied or not. Is this clear, this clarification discussion? Great. Now, once we have an inclusion dependency that is applicable to a set with U, what do we want to do now? We want to define the new atom that we want to add. Because if sigma is applicable, it means that we have to apply it with this witness U and add a new atom. What will be this new atom is defined here with this, I denoted by new sigma U, which will be a P atom of this form, where, let's see now how these variables look like. I think it's clear what's going on. Now, the L variable there, so if L is actually what is a position, is one of the positions in J1 up to JK, right? So if L is JR, right? Then the variable VL is essentially the variable UIR in there. It's the variable that I need to somehow reuse because that's what the inclusion dependency tells me, right? So the Lth variable in here, it will be UIR, which comes from the tuple U, okay? Is it clear what I'm saying? So these are the variables that essentially I need to propagate from the R atom to the new P atom at the right position. Now, for all the other positions, for all the other positions in P, which are not positions in J1 up to JK, there are the positions without any constraint, and there are the positions that we are going to put a fresh variable, which we haven't used before. And now here, what I do is the following. Usually, if you open a textbook or if you read a paper, usually people there say just pick a variable without specifying what is this variable or the name of the variable. Just pick non-deterministically a variable from our infinite set vars and just plug it there. That's it. What I'm doing now here is a bit different. What I'm doing here is actually I have a mechanism which tells us precisely what is the name of this variable. Right? I want to prefix the name of the variable that I plug there for a good reason again, and we will see that later. And actually, the variable of the name of the variable is determined by the position L and the inclusion dependency sigma and the witness U, which means that once I give you the position and sigma and U, then I can this uniquely determines the name of the variable that I will plug there. Now, the name itself is not so important. As I said, one could pick some other variable there, or one can come up with a different mechanism. The only reason why I did that is to have a deterministic way of giving variable names to these variables, okay? And again, the position, sigma and U, uniquely determines the name of the variable that we will plug there, okay? And of course, this is a variable coming from the countable infinite set var, and it's a variable that doesn't appear in terms A. It doesn't appear in the set of variables in the set A. Okay. And once we have this new atom in place, so we know now how this new atom looks like, the chase step, it's pretty clear what is the chase step. The result of applying sigma to A with this witness U, it will be what? It will be the set of atoms A prime, which is obtained by simply adding this new atom to A. And that's it. So each chase step then adds one new atom, which is defined in this way, depending on sigma and U, to the current set of atoms A, and it will give us this new A prime. And similarly to what we did for functional dependencies, this is how we denote a chase step. So A prime is obtained from A by applying sigma to A with the witness table U, which essentially means A prime is obtained from A by simply adding this new atom. So don't be scared with this weird thing. As I said, this is just a way to prefix the name of these fresh variables, right, by exploiting the position, sigma, and U. Okay, and I will come back to why I'm doing this in this way in a while. So this is a single chase step. So let's see again in our example the steps. So this is what we have seen before. And now you can see that in this case, sigma is the first inclusion dependency. And here we have the witness table, which is x1, x2, x3, right? So this gives rise to a single chase step. So from this, we apply this functional inclusion dependency to the given set of atoms with this table, and we get this new set of atoms. Now here I cheated a bit, so y1 and y2 should follow this naming scheme, but because it will be a mess on the slide, I just avoided. I tried, but it was a mess. So imagine that y1 and y2 here follow this naming scheme, right? Which means it will involve the position, sigma, u, it will be something very long. So imagine that it's like that. So you see now what is a single chase step, right? And now, having the notion of chase step in place, let's go to, again, what we did for functional dependencies, to the notion of sequence, right? Because one single chase step, okay, it's there. Now we have to apply this iteratively, starting from the given set until there is nothing else to do. Now, let's start with the finite case. So a finite chase sequence of A under sigma is a finite sequence of atoms, where the first set of atoms in there is A, good. The second bullet tells us precisely what we discussed for functional dependencies. So AI plus 1 is obtained from A via a chase step, right? So for each I, we can find some inclusion dependency in sigma and some atom in AI, such that, and here we have to be a bit careful, such that, of course, AI plus 1 is obtained from AI by applying sigma to AI with U. But here I have an additional condition which says that this new atom that I will produce from sigma and U is not in AI. What does this mean? It means that I have not already applied sigma on, what is the terminology I forgot? Sigma to A with the witness table U. So here, essentially, we are saying that I will apply this chase step, providing that I haven't already applied this guy before. I don't want to reapply a chase step. One may say, okay, what's the problem? You are building a set in the end, and then you just an atom in the set that already exists. True, but if I don't pose this condition, then I can now build infinite sequences for a wrong reason. I can just keep repeating there the same chase step again and again and again forever, right? Without affecting the set that I'm building. But if I don't pose this condition, it will be a valid sequence, an infinite one, and I will have to deal with this thing. So here we are only saying that I apply a functional dependency to A with U, providing that I haven't already applied this guy. Is that clear what I'm saying? Great. And the last bullet essentially tells us that there is nothing else to do. So for every inclusion dependency, an atom RU in A, this atom is already there. So I have already applied sigma to A with the witness table U. And there is nothing else to do. So which means AN, which I define as the result of this finite chase sequence, is a set of atoms that satisfies the inclusion dependencies. Okay. So this is the finite case. Now we have to define also the infinite case. And in this case, we really need it. For functional dependencies, we defined that just for the sake of completeness, and then we discarded it because we realized that there are no infinite sequences. But here, actually, infinite sequences exist, as we have seen. And we have to properly define them and deal with them. So what is an infinite chase sequence of A under sigma? Is an infinite set of atoms starting from A. A is A0. The second bullet is exactly the same as before. AI plus 1 is obtained from AI by applying a chase step, providing that this same chase step has not already applied. And here is the third bullet, which is very, very important. in the case of infinite sequences, which we need to understand what this guy tells us. This guy essentially tells us intuitively the following. If a certain chase step is applicable at a certain point, right, eventually should be applied. So if at a certain point of this chase sequence or of this chase procedure, there is a functional dependency sigma, which is applicable to a certain set with some weakness, even if I don't decide to apply it at this point, in the future, at some point, I should apply it. This is what this condition, which we call fairness, tells us. So formally, it says the following. For each I and for each inclusion dependency, an atom RU in AI, such that sigma is applicable to AI with U, which means that at the ith step, sigma is applicable with U. So for each such case, there must be J greater, can be also equal, because right now. So, but there exists some J such that this atom belongs to a J, which means that there must be some step J step after I that eventually this guy will be applied and generate this atom. Now, one may ask, why all this hassle now about this fairness condition? So can someone imagine why we need that? Can someone tell us why this is important? Yes?
Well, I mean, it's like if you imagine like shadowing the way you apply your inclusion dependencies, you could just enter an infinite loop,
Great.
just want to choose one or two
Yeah.
to apply, and it just maybe there's just that one rule that will
Perfect.
really help you out, and that it doesn't.
Very nice. So that's precisely the point. Since we have infinite sequences now here, take this example. So the first inclusion dependency there, it will force me to build something infinite. But I can keep applying now this guy and fall in this infinite branch, right, forever, and never apply the second TDD, the second inclusion dependency, which is applicable. So at each step here, if you see, this guy is applicable, right? I should generate some p atoms here. But if I don't pose the fairness condition and I just stop at the second bullet, this guy here will be a perfectly valid chase sequence, right? Because it starts from from A, great, and the second bullet is satisfied because each step it's a valid chase step. But in the end, what I will build there does not satisfy my set of constraints because I will never treat the second inclusion dependency in there. So I have this, I mean, it is possible without the fairness condition to fall in such an infinite branch and forget some inclusion dependencies. This is not the case with finite sequences. Finite sequences are by definition fair, right? Because at some point I will reach a point which there is nothing else to apply, right? So this is why we need the fairness condition, right? So all the versions of the chase with inclusion dependencies or generalizations of inclusion dependencies, they need to impose the fairness condition. Otherwise, what we build there is not even a set of atoms that satisfies the set of constraints. Right? And now the result of such an infinite sequence is essentially the infinite union of all the intermediate sets of atoms. So it's this union here. Okay. Good. Now let's see. So this is the chase. So let's see now the key properties of this chase procedure for inclusion dependencies. So similarly to what we did with functional dependencies. So here now, it's clear that we have both infinite and finite, right? Now, the question that pops up is it possible that some sequences are finite and some sequences are infinite? That's a good question. And as you can see here, we can prove that all chase sequences are either finite or infinite. So either all of them are finite or either all of them are infinite. It's not possible that some of them are finite, some of them are infinite, some of them are infinite. Now, why this is true? This is true because, let me go back, sorry for that, because of the way that we define the applicability condition. If we were using the restricted chase, for example, which means that sigma is applicable only if it's not violated, right? There, this property doesn't hold anymore. So with this more clever notion of applicability, which gives rise to the restricted chase, it might be the case that some sequences are finite and some sequences are infinite. And intuitively, to understand this is because the order now that you apply there, the inclusion dependencies with this more sophisticated applicability condition really matters, because what I apply now, it may affect future applications. I may generate something now which will satisfy things and avoid some future applications, but the different order may force me to go forever. So this is with the more sophisticated applicability condition. If we stick to this simple applicability condition, then we can really prove the first bullet, which means either everything is fine, all the sequences are finite, or all of them are infinite. Okay. The second point tells us that it doesn't matter in which order we apply the inclusion dependencies, right? In whatever order we apply these guys, we will always lead. We will always get the same result. So if I have two finite sequences, AN and BM, which are the result, is the result of these sequences, will be the same set. If I have infinite guys, the infinite unions will be the same. Now again, here one may say, if you open a textbook and read that, you will not see this property, because usually there, the way that we choose these new variables is not predefined, right? There you choose some fresh variables, and therefore the only thing that you can say is that the sets of atoms that you build are isomorphic, not equal, but are isomorphic. Here I can state equality. Why? Because I prefix the way that I name variables, right? I hope you can see what I'm talking about. So the fact that I fix the naming scheme, it allows me to state this as an equality, set equality, and not just isomorphism, right? Which means no matter how the order that we apply the inclusion dependencies, we'll get exactly the same sets of atoms. And therefore, we can refer to the unique result of the chase. It's a unique set of atoms, which I denote in this way. Of course, this set of atoms satisfies sigma by construction, okay? Of course, this may be an infinite set, but if we take the limit, this guy is a well-defined set of atoms which satisfies sigma. And finally, we have the key property similar to the one that we have seen for functional dependencies. So consider a set of atoms A prime such that A can be mapped via homomorphism to A prime, and some tuple U maps to B. And in addition, A prime satisfies our set of inclusion dependencies. Then for every such A prime, we can show that the chase, the set of atoms that the chase builds, can be homomorphically mapped to A prime by respecting the fact that U is mapped to B. Okay. This is the representative property that I discussed a couple of times, right? And now the point is, with this simple naive version of the chase that I call oblivious, right? With the simple applicability condition, already with this simple definition, we can achieve this last property. So we don't need this more clever applicability condition, which applies inclusion dependencies only if they are violated to achieve that. We can achieve this universality, let's say, property, or this representative property, even with this naive, oblivious version of the chase. And that's why we usually use that version, because it's simpler, technically speaking, to work with, right? Since we have this key property in place. Please. Now, imagine that imagine that an inclusion dependency is applicable only if it's violated. So imagine that you have this inclusion dependency. Maybe it's a mistake that I didn't add an example. So this is our notion of applicability. As you can see here, we say sigma is applicable just because there is an R atom. Just because there is an R atom, I say it's applicable. But I didn't check here whether there is also a P atom that satisfies the inclusion dependency. Now, the more sophisticated applicability notion will check, okay, I have this R atom, but there is no P atom that satisfies, in the end, my inclusion dependency. Right. This is what I mean, more sophisticated applicability condition. And this is the condition that gives rise to the restricted chase, right? The standard version of the chase, what people call the standard version. Now, with this standard version, yeah, it's more clever. It terminates more often. It builds smaller sets of atoms. But on the other hand, you lose some nice properties like all sequences are either finite or infinite. Essentially, this is what you lose mainly, right? And sorry, Jorge. And as I said, no matter which version of the chase you use, you will eventually manage to prove the key property, this universality or representative kind property, which is what we need. And therefore, usually we just use the oblivious instead of the restricted chase because it's just easier to work with. You don't have to take into account explicitly this more sophisticated applicability condition. Jorge.
There is a part of the chase process where you don't apply if the new tuple is already in the.
Yes.
Yeah. So actually, why is this restriction not in the applicability?
No. The applicability condition. Okay, let's try to understand this.
This is why.
So here, no. This guy, it's different. This guy simply says that I haven't already applied this particular step, right? But this is orthogonal to the applicability condition. I mean, whether sigma is applicable to alpha with you, this is the applicability condition that tells me that. And now once I'm applicable, depending on the applicability condition that I decide to choose, then this gives rise to a new atom. And here I'm just saying, whenever you are applicable, you apply it only if you haven't applied this before. So these are orthogonal things.
Yeah, but this restriction is what makes sense with the definition of applicability. In the case of functional dependency, you always apply whenever it's applicable. So this is the main difference.
So the way that we define it with functional dependencies is more in the spirit of the restricted chase. Because there we said we apply a functional dependency only if it's violated. I hope this clarifies things. So if you think of the functional dependency case, there it was more in the spirit of the restricted. Okay, and this is usually the standard chase that we use. Here you have all these differences that give rise to different versions of the chase with this, anyway, these low-level details that one should understand. But the message that I'm trying to convey, we can use the oblivious, which is the naive, the simplest version, and this is good enough for our purposes because we get these nice good properties and we can prove the last bullet, right? That's what I'm saying. One could use the restricted, but I don't use it for the reasons that I explained. It's just more difficult to work with and we don't need it. Now, in applications where termination is important, or in applications where you want to really terminate often, like, I don't know, data exchange, for example. In data exchange, for those who are familiar, there you need the restricted chase because the standard language, which people call weak acyclicity, right, which terminates with the restricted chase. If you fit the oblivious chase with a set of weakly acyclic rules, for those who are familiar with these things, there is no guarantee that the oblivious chase will terminate. So there are applications where the termination matters, and there, yeah, it's better to use a more clever version. But for our purposes, the oblivious one is enough. So I think we discussed a lot about that. We should go on, unless there are questions. Yes?
There exists a set of balances that it's impossible to build a fair
No, the fair, I mean, you can always come up with a sequence which is fair. I can give you this fair, it's just not easy now, but there is always a way to devise a fair chase sequence. Actually, there are more than one, but there is always one. I can give you now one. So for example, you can start from the given set and obtain whatever you can obtain from the given set. So without going on. So imagine that the given set is level 0, right? Then whatever you can obtain from the given set is level 1. So you saturate level 1. Then you saturate level 2, which means whatever you can get from level 0 and level 1. So you construct you build a chase sequence which goes level by level in this way, level by level. I hope it's clear what I'm saying. This is clearly a fair sequence. So there is always a way to build a fair sequence. Perfect. And now let's go on. We are running out of time, but it's not a problem. Now let's go on to do what we did for functional dependencies. So remember, we use the chase there to characterize implication. But now here we have a bit of a problem, and we have to be careful. The only thing that we can characterize now with this chase is what I call here unrestricted implication. What is this unrestricted implication? So sigma, a set of inclusion dependencies, implies some other inclusion dependency without restriction, which I denote in this way, if it's exactly the same definition, but now we consider not only finite databases. Recall, by definition, a database is a finite object, right? A database is a finite set of tables, and each table is finite. Or in other words, it's a finite set of relational atoms. But here now, with the chase that we just developed, right, the only thing that we can characterize is implication where both finite and infinite databases are taken into account. And this is what I mean by unrestricted. It means that also infinite databases now come into the picture, right? And in principle, it's that the unrestricted implication and the restricted one, in the sense that only finite databases are considered, are equivalent. In general, this is not the case, right? Of course, one implies the other immediately. So the fact that if sigma implies sigma in an unrestricted sense, then of course it implies in a finite sense, in a restricted sense, but not the other way around, right? In general. Which means now, with the chase that we have defined, because the chase may build an infinite set of atoms, nobody guarantees its termination. The only thing that we can prove is this proposition. So we can prove that the unrestricted implication is equivalent to this statement here. The chase of this prototypical atom that violates sigma under the given set of inclusion dependencies satisfies the inclusion dependency sigma. Is it clear what I'm saying here? But this is not very satisfactory for us, right? Because our goal was to solve the implication problem, which focuses on finite databases, right? So what do we do now? Now, to get rid of this or to bypass this problem, we have to invoke another interesting result, which I will not even try to prove, but at least state it, which is called the finite controllability of logical implication for inclusion dependencies. This theorem essentially tells us that inclusion dependencies is one of those nice cases where the restricted and the unrestricted version of the implication are the same, are equivalent. So the set of inclusion dependencies entails sigma in a restricted way, in the sense that only finite databases are considered, if and only if the same holds in the unrestricted case, which means both finite and infinite databases are considered. This is not true in general, but inclusion dependencies are well behaved and allow us to prove this thing, which is called finite controllability of logical implication. And of course, now if we put these things together, since we characterized unrestricted implication via the chase, and since we have finite controllability in place, we will get immediately a characterization of the restricted version of the implication, which means only finite databases matter, which is what we are interested in, via the chase. Okay. Good. So we didn't have to get into finite controllability things in the case of functional dependencies. Why? Can someone say why? Because there the chase is always finite and it always builds this finite representative. Here, the chase doesn't build, in general, this finite representative. What it builds there is an infinite guy. And therefore, we can only talk about the unrestricted version of implication, right? But because of the finite controllability result, we can get this. So there are some questions, yeah. Well, I mean, there are examples of that. I mean, yeah, look, we can get this offline. Maybe someone can have a quick answer, guys. I mean, we're final. Yeah, perfect, good. Yeah, great, yeah. So if you combine inclusion and functional dependencies together, imagine that you want to study the implication problem, not just for inclusion alone or functional dependencies alone, but together, right? So you consider a set of inclusion and functional dependencies. Thanks, Diego. This is a case where this result doesn't hold. And we can prove it later together if you want. Okay? Which means this machinery in the case of, actually, if you combine the two, it's even undecidable. So let's forget about it. But this is a case where the finite controllability fails. Okay. Good. So the chase is still a useful tool for studying implication here. And now one may say, great. So we have the chase, blah blah blah. Let's apply this algorithm. Is this an algorithm now? Please, yeah. Mm-hmm.
In general for TGD or especially for
so for TGDs, no, it's not true. For TGDs, this fails. I mean, okay, Diego can correct me, but once you are able to express transitive closure things, right? And with TGDs, you can easily express transitivity. You can write RXY and RXY and RYZ implies RXZ. Once you are able to express such kind of things, right, then you are in a dangerous territory. And this is actually what you exploit with functional dependencies and inclusion dependencies to prove that this breaks, because equality is transitive, and you exploit that, if I remember well, right? So yeah, if you go all the way up to TGDs, this is not true. So you really exploit the well-behaved nature of inclusion dependencies. It's not for free, and it's not an easy result. Okay, so do we get an algorithm now here, guys? This is a question to you. Okay, we just said that we worked a bit here, and in the end, we managed to characterize implication via the chase. Do we get this algorithm as we did for functional dependencies? Are you happy with that? Why? Can someone say something to give me 10 seconds to drink my water? Sorry? Okay, the chase might be infinite. We said that several times. So this is not an algorithm. So I cannot just build the chase. Now, if I have a set of constraints there, sigma, that guarantees the termination of the chase, then one may say, yes, this is a decision procedure. But there is no such a guarantee. So we have to do something a bit more clever here. And I will not get into the details of this thing now, but I think I can share with you, can convey the essence of that. So let's try to devise an algorithm now, which will of course exploit the chase, but without explicitly building it, right? Because we cannot afford that. So we are given a set of inclusion dependencies and this guy. Now, from our characterization, from our characterization here, what we need to do is to check this. Explicitly building this guy, as we said, is not possible. Now, let's see how we're going to do it. Now, this check essentially boils down to what? Recall that this violate sigma is just a single atom, Rx1 XL, right? Which means that this task here, whether the chase satisfies sigma of this form, essentially boils down to checking whether this set of atoms, which we built via the chase, contains a p atom where this projection, this equality here holds, right? So starting from Rx1 XN, essentially the question is it the case that the chase eventually will produce an atom Py1 up to Yn where this equality holds? This is essentially the question, right? So checking for satisfiability here essentially asks for that. Does the chase builds or generates an atom of this form? Do we agree with that? Now, again, building the chase explicitly and then check whether such an atom exists is not the way to go. Now, the way to go now is to somehow non-deterministically try to build a sequence starting from the given atom in the following way. So we start from our atom Rx1 XL, right? There, I can guess the next step, right? Guess some functional dependency which is applicable to this guy and generate a new atom, right? We generate now this new atom. Now I can forget the previous atom. I don't really need to remember what was the previous atom. Now I have my current atom and I can continue non-deterministically building this thing. So I guess another chase step, I build a new atom, I forget the previous one, and I go like that. And this heavily relies on the shape of inclusion dependencies, in which sense each atom that I generate in the chase depends on one atom. I don't need, right? It's just one atom that Each atom depends on another, on one atom. If I had a conjunction of atoms in the body, like TGDs, this doesn't work anymore. But since I have this kind of linearity where each atom depends on one atom during the chase, I can build this sequence step by step, right? By just forgetting the previous atom and keeping the current. I hope it's clear what I'm saying. I proceed like that non-deterministically. And at some point, I decide again non-deterministically to check, is the current atom that I have, is the current atom that I have in my hands the atom P that I'm looking for? If yes, great, true. If not, we fail. And of course, the non-deterministic algorithm that I just described, if there exists such an atom, we'll eventually find it. Now, why is this a good algorithm for us? I think, or I hope it's clear that this is a sound algorithm that I just described. And also the fact that I don't have to remember the whole history, only 2 consecutive atoms, right? In the end, this algorithm guarantees that we don't really need a lot of space. So in the end, this algorithm will allow us to prove that implication of inclusion dependencies is feasible in polynomial space. Okay, not time, space, right? And in fact, we can prove that this is the best that we can do. One can complement this upper bound with a lower bound and show that this is a p-space complete problem. Now, the lower bound can be proved in several ways. I mean, one can simulate, for example, a deterministic p-space Turing machine, right? And there are several other proofs out there, which I will not get into. But what I'm saying is that this procedure that I just described, which gives a p-space upper bound, it's a worst case optimal upper bound. Right? So there was a question somewhere. Yeah, please.
I was just curious to understand if this space upper bound is obtained by some automaton.
No, you could. I believe that you could, but the algorithm that I just described, it's really a chase-based algorithm by non-deterministically building this portion of the chase, right? And that's it. But
so you just say, yeah, you just store all the.
No, but I don't store. But I don't store all of them. That's the point, because I can't afford to store all of them, because I may have to generate a very long sequence. Nobody guarantees that starting from Rx1, Xn, after polynomially many steps, I will find this atom if it exists. So I cannot store the whole history. That's why I said, once I generate an atom, I can forget its parent, right? Which means at each step, I need to remember 2 atoms, right? And this is what allows me, of course, a lot of details are missing, but the essence is that this is what allows me to get the p-space, right? Please.
Does it mean that every atom that I can generate in this case, there is a way to do it in exponential length case?
It means that after exponentially many steps, right? So put it differently. If there exists such an atom, this will be derived after exponentially many steps. If you don't derive it, then of course, nobody guarantees that the chase terminates after exponentially many steps, because the chase may be infinite. But this tells us that if you don't derive this guy after exponentially many steps, then there is no way to derive it. This is what it tells us. So I can provide a bound on the depth, whatever that means to you now, but I hope it's intuitively clear what I mean by depth. So I can provide an exponential bound on the depth of the chase and say, if you don't generate this atom up to this exponential depth, then there is no way to generate it after that, and then you can just stop. But if you build this thing, it will be very large and very costly, so it will not give you a p-space upper bound, right? So to get the p-space upper bound, you really need this non-deterministic process that I just described. So if you explicitly build this chase up to a certain bound, it will be very costly. It will be exponential time at least.
I mean, you only have a fairness condition, right? So, I mean, this is implication you have. For every atom, there exists a sequence in which the atom will appear, but it's not necessarily that all sequences will. If you take the first exponential atoms of every sequence, it may not be that they include all the necessary atoms.
I'm not sure. Sorry, sorry, Diego.
That you apply.
Yes.
A lot of time the same branch of the rules,
right?
And you change the other one. I mean, this fairness condition, they. That eventually we switch.
I'm not sure.
No, the algorithm is fine. It's just the statement about
No,
after exponential.
yes.
I think it's like.
No, actually, it's not exponential. You're right. Now I got it. It's not really exponential steps. It's actually the exponential depth of the chase. I'm talking about the depth. So if you see the chase as a tree, right? I'm talking about the depth of this tree, not the number of chase steps. The number of the actual number of chase steps may be way more, right? Okay, now I got it. I hope we agree on that. Great.
But this tree that you said is finitely branching, right?
Yes, it is.
Like at exponential steps.
No, look, the depth of this tree, if you see the chase as a tree, right? The depth is exponential, but the whole thing that you are going to build there is double exponential in here. If you explicitly build the chase, I don't have a marker too. Is there a marker here? Oh. No, I'm just talking about this naive algorithm based up to this depth, right? Of course, you can convert this into exponential time algorithm, but this algorithm is not the one that we are talking about now. So what I'm saying is the following. So if I start from this atom, right, and you see, I hope, do you see what I'm writing? I was sure. Now, no. Okay, guys, I can't do much. So imagine a tree, right? This is the chase. The chase essentially, if I have an atom, it generates another atom. Of course, from the same atom, I generate several atoms, right? This is what I mean. Imagine the chase as a tree. Of course, this guy can be infinite. I can naturally define the depth of this tree. And now what I'm saying is, with inclusion dependencies, I can show that there is some depth k, which is exponential, right? Which says that if I cannot generate this atom up to this depth of the chase, right? Then there is no way to generate it after this depth. But I'm talking about the depth of the chase. Now, if I apply, of course, if I have this depth in place, this gives me a deterministic procedure. Just build the chase up to this depth, and then check whether your p atom is in there. But if I do that naively, I will have to spend double exponential time because I will have to build a tree of exponential depth, right? This is the algorithm that I was talking about. Of course, you can convert this p-space machine into an exponential time. That's fine, okay. But I think the idea or the question was whether this means such an exponential depth on the chase.
My question is about finiteness. To restate what you said, is it okay to say every atom of the chase will occur in this exponential depth?
Yes, this is true. But depth. Okay, every atom, it will be generated up to this depth. But you may need more chase steps, not just exponentially many, but way more chase steps to generate it. Because already, for example, take depth 1, you have several atoms, right? The last atom in there, it may take a lot of chase steps until you generate it, but it's still depth 1. So the depth doesn't coincide with the number of chase steps. That's what I'm saying. But let's take this offline. It will take forever. But I hope in general it's clear what I'm trying to describe here. Okay, so concerning the two problems that we have seen so far, and I doubt that we'll have time to go. Okay, maybe we have a bit more time. So we have seen the satisfaction and the implication problem. Concerning the satisfaction, things are rather easy, I would say, just implement the semantics. We have seen that. Now, in the case of implication, we rely on this chase characterization, right? It's always this business here. We start from this prototypical set that violates our function dependency or inclusion dependency, and we convert it into this representative guy via the chase. We simply need to check that. So we just followed the same approach in both cases. But there is a key difference between function dependency and inclusion dependencies. In the first case of this, we can explicitly construct the chase, because after polynomially many steps, as we discussed, this will terminate and give us this finite set, and then just check for satisfaction. So things are rather simple there. In the case of inclusion dependencies, we cannot afford that. We could apply such a thing, but this will never give us the p-space optimal bound. So we need this more refined non-deterministic procedure for doing that. And here I stress the fact that the machinery for inclusion dependencies heavily relies on the finite controllability. of logical implication. Without that in place, imagine that for some reason we don't have finite controllability, then what I discussed today, and this p-space upper bound, works only for the unrestricted version of the implication, which means both finite and infinite databases. So without finite controllability in place. But since we have it, we can use it and get also the result for the restricted version, which means only finite databases only finite databases matter. Okay, so this is what I wanted to present concerning these problems. And okay, as you understood, one of my goals was actually not just to see the complexity results of these problems, but also to discuss about the underlying tools, which were the chase in both cases, which was the case in both cases. And I hope that you have a good idea now what this chase does and why it's a useful tool. Now, in the remaining time, so how much time now do we have, Diego? 20 minutes, let's say? 20, great. Okay, great. Okay, now, at the beginning, if you remember, at some point I said constraints play a role in query optimization, right? I said something like that. And I would like to come back to this and try to discuss with you how, what I mean by that. And in particular, what I would like to discuss with you is how integrity constraints help static analysis of queries, and in particular, containment of queries, which is a crucial task when it comes to optimization, right? Please. Yes.
When you have improvement, you say something when you consider the
I don't know. Yes, actually, I don't know if Diego was involved in that. So in the ontological setting now, right, people actually studied in this OBDA, or ontology-based data access, which is not very far from what we're discussing. It's just a different setting. There, people actually consider the bug semantics, but I don't know if Diego was involved or the Oxford guys did that. I don't remember. Okay, so there are some results for a description logic, which is actually inside inclusion dependencies, DLite, if you know that. So, and there are some works there, but unfortunately, I'm not in a position to say much. But people consider that, yeah. In general, I avoid bug semantics. So what I was saying is that I would like to discuss with you how constraints affect the static analysis of queries, and in particular containment, right? Now, to do that, I would like to concentrate on a key query language. So to illustrate what I'm saying, because my claim here is that indeed constraints help containment, right? Which is, as I said, a static analysis task. To illustrate that, I will focus on a key query language, which I'm pretty sure you all know, which we call conjunctive queries. So what are conjunctive queries? It's essentially, you can think of it as the select project join fragment of algebra, or as calculus queries without negation, universal quantification, disjunction, and equality, or select from where SQL queries, right? So it's a very simple language, but an important one that has been studied a lot, right? So just to be a bit more precise, a conjunctive query looks like that. It's just a conjunction of atoms. So R1 up to Rm are relation names coming from some schema. All these X, Y, V1, Vm, these are tuples, right? It's bold-faced, maybe it's not very clear. So these are tuples or variables. Imagine these are variables coming from our var set. In addition, all the variables in these VIs either are existentially quantified, which means they appear in Y, or they are variables in X. And these variables in X are what we call the free variables because they are not quantified. And sometimes these are called distinguished or output variables. As we shall see in a while, these are actually the variables that determine the answer to our query. So this is how a conjunctive query looks like. It's a very simple language. And it is very convenient actually to see these queries as rules. So we can equivalently express this query as a rule of this form. This weird symbol, you can think of it as an arrow. And essentially it states that if this holds, if the body of the query holds, then we expect to get something as an answer. You can read of it in this way. So, but let's stick to the syntax for a second. So this is the syntax, and from now on, I will use this rule-based syntax, okay? Which means that we can very conveniently see the atoms in this query, the body, as a set of atoms, right? So which means from now on, if I refer to the set of atoms in a conjunctive query, don't be surprised. I refer to the body, to the set of atoms in the body. Now, how we evaluate such queries? Okay, let's see this by an example. So this is the same query that we have seen before about this direct flight from London to Glasgow. And the calculus query that we have seen, I don't know, 2 hours ago, it's essentially a conjunctive query, which can be expressed as a rule in this way. So I'm looking for an airport in London and an airport in Glasgow, such that there is a direct flight from X to Y operated by Z. And as you can see now, Z is my output variable, right, which will determine the answer. Now I was careful enough to change this, and now the LGW is gone, so Larnaga has the right code, right? So if we say here U2 now, it will be an answer that we can trust. And so how we evaluate such queries, it's essentially a pattern matching problem. We need to find a way to match, because you can see the body as a pattern, and we need to match this guy into our database, which, as we said, can be seen as a set of relational atoms. How this matching notion is formalized, it's a homomorphism, right? It's a homomorphism from the set of atoms in the query to the set of atoms in the database. And here is such a homomorphism, right? So here you see the function, and the image of Z, which is U2, Z is mapped to U2, is actually an answer to our query. So each such homomorphism gives rise to an answer, and in the end, the answer to our query is a set of tuple. That's it, okay? These are conjunctive queries. You don't need to know more than that. All right. Now, a crucial task which, as I said, is important for optimizing queries. And of course, we study this for whatever query language, but here I will concentrate on conjunctive queries, is containment, right? So given two conjunctive queries over a certain schema, we say that Q1 is contained in Q2, which I denote in this way, Q1 contained in Q2, if what? If for every database instance D of our schema, the answer to Q1 over D, denoted in this way, is a subset to the answer of Q2 over D. So here I can use subset relation because, as I said, the answer to a query is a set. It's a set of tuples. So the set of tuples which is in the answer of Q1 over D is a subset of the set of tuples which is an answer to Q2 over D. And this, let me stress that this is for every database, right? For every finite database instance of S. So it's a strong statement, right? So Q1 containing Q2 involves infinitely many databases, right? It's a strong statement. This is containment. And a very interesting task related to this notion is checking for containment, right? So we get as an input two conjunctive queries, and the question is whether Q1 is contained in Q2. Now, one may say why we care about that and why we want to study this problem and how this relates to optimizing queries. So what I can say here is this. So usually when we optimize queries, the goal is to replace a certain query with some other query that it's easier to evaluate. So I want to replace Q1 with Q2 because I know that Q2, it's easier to evaluate, right? Its syntax is, I mean, I can massage Q1 into something else, which is easier to evaluate. But of course, during this process, I don't want to change the meaning of my query, right? So which means I have to be sure that the new query that I know how to evaluate, it's more efficient to evaluate. I have to be sure that it has exactly the same meaning as Q1. Or in other words, it gives exactly the same answer over every database, right? But in the end, to check for that, what I need to do is just two containment checks, right? So this is how this static analysis task of containment comes into the picture when we talk about optimizing queries, right? Because it allows us via these two containment checks to check whether two queries are equivalent, right? And therefore, when I optimize my query in whatever way, I can, in principle, check whether the new query has the same meaning as the original one, right? All right, so this is containment. As I said, this is not only about conjunctive queries. The containment problem has been studied for several other formalisms, right, and several other query languages. But here, we focus on conjunctive queries. Now, how we do that? Again, as implication. It involves infinitely many databases. So it's not that I can enumerate all the databases and now go through all of them and check whether the containment holds, right? We need something more clever. And this more clever thing involves what we call query homomorphisms, right? So a query homomorphism from conjunctive query Q1 to Q2 is essentially a function from the terms in the body of Q1 to the terms in the body of Q2. So terms, variables, and constants, I mean, such that age is a homomorphism. So recall the notion of homomorphism that we discussed a long time ago. It's exactly the same notion. So age is a homomorphism from body 1 to body 2. Recall that these bodies are sets of atoms. So I can talk about homomorphisms. So it's a standard homomorphism, but in addition, we want to respect the output variables, right? So the key point in the notion of query homomorphism is that if I apply this homomorphism to the output table of Q1, what I get is the output table of Q2. Okay. So again, it's just a plain conditional condition that it respects the output tables. And why is this a useful notion? Because now we can prove this famous theorem. So it's an important theorem in database theory, which essentially characterizes containment of conjunctive queries. So it tells us that Q1 is contained in Q2 if and only if there is a query homomorphism from Q2 to Q1. And as you can see here, I changed the order. This is not a mistake. This is how it works, okay? So Q1 is contained in Q2 if there is a query homomorphism from Q2 to Q1. And this is a characterization. This is an if and only if statement, right? So the existence of a query homomorphism implies that the containment holds. The non-existence implies that the containment doesn't hold, right? So it's a strong result. Not very difficult to prove, but it's a very useful result. Here is just an example to illustrate this notion. So imagine that we have these two queries. So I think it's clear that this H is a query homomorphism. So we can map the body of Q2 to the body of Q1. And at the same time, we respect the output tables, right? So we can conclude that Q1 is contained in Q2, but there is no homomorphism from Q1 to Q2. So for example, there is no way to map the atom SZZ to an atom in Q2, right? So there is no homomorphism at all from Q1 to Q2, which actually allows us to conclude that Q1 is strictly contained in Q2. So this is how one can use the homomorphism theorem and conclude such kind of statements. Okay. Great. And having the homomorphism theorem in place, we can even study the complexity of this problem. So for the upper bound, we can easily get NP because you just guess and verify, guess a function and verify whether it's a homomorphism. And both guess and the check step can be done in polynomial time. And the NP hardness, there are several proofs out there. One can reduce, for example, from 3 colorability, right? And this is for the existence of a query homomorphism. And since we just said that, containment and the existence of such a homomorphism is the same thing, that's what the homomorphism theorem tells us, we can conclude that CQ containment is an NP complete problem. Okay. Well, that was a crash course on CQ containment. Now you know everything about containment of conjunctive queries. Now, where are constraints now here? So I put constraints aside for a few minutes. Let's come back to constraints now. The question is, does containment benefit anything from constraints? Because in all this business of containment that I just described, I didn't mention constraints at all. I didn't take into account constraints at all, right? But it seems that if we take into account the constraints, then we can gain something in the sense that queries for which the containment doesn't hold, now suddenly if we take into account the constraints, the containment holds. So let's see why. So let's see an example. So imagine that we have these two queries over this simple schema, right? It's clear that there is no query homomorphism from Q2 to Q1. There is no way to map RYY to something in the body of Q1. So there is no homomorphism at all from Q2 to Q1. And the homomorphism theorem allows us to conclude that Q1 is not contained in Q2. Now, assume that we focus on databases that satisfy this simple key. right? So imagine that we don't care about all that. So we restrict the space of databases that we are interested in. And for us, a database is valid only if it satisfies this key constraint, this functional dependency. We don't care about all the other databases. For us, these are invalid but databases that we discard. Then it's very natural to ask whether containment holds only for those databases, right? That's the question. And do we gain anything now in this case? And the question is yes. Actually, if we forget about all the other databases that they don't satisfy this functional dependency, then in this case, the containment holds. So, and let's see why. Take this query Q1. If you think about it, if this query is satisfied in the sense that if we can map this query to a database, and recall our databases satisfy this constraint, it means that we can safely conclude that Y and Z, right, are mapped to the same symbol. Because as you can see, these two atoms, the first and the last, they have the same variable at the first position, right? But because of the functional dependency, we can safely conclude that Y and Z, they will always be mapped to the same symbol. Do you agree with that? Perfect. Which means that somehow one can say, look, I can massage a bit this query by unifying Y and Z. And what I will get, it will be an equivalent query, providing that we care only about databases satisfying this constraint, right? In general, it's not if we consider arbitrary databases. But if we focus only on databases that are consistent with this constraint, then unifying Y and Z, it's a harmless thing to do. But in this case, there is a homomorphism from Q to Q1. Actually, in this case, we get exactly the same query, right? So this is a very simple example which illustrates that although containment among queries may not hold in general, if we reduce the space of databases that we are interested in, right, by taking our constraints into account, containment may hold, right? So we can discover more cases then where containment holds. And the same for inclusion dependencies. I will not go through this example. It's an example with inclusion dependencies that illustrates exactly the same thing as here, that if we take into account the inclusion dependencies, containment now holds, although with arbitrary databases, it doesn't hold. Now, having this in place, it's very reasonable to revisit the notion of query containment then, of containment of conjunctive queries by taking into account the constraints. And this is what I do here. It's essentially the definition of containment, but now under a certain set of constraints. And the definition is what you expect. We say that Q1 is contained in Q2 under sigma if this containment holds for every database that satisfies sigma. So the only difference from the original notion of containment is that now I consider only databases that satisfy sigma. That's it. And the next obvious step is to understand these two problems, right? Now we are given two queries and a set of constraints, either functional dependencies or inclusion dependencies. And the question is whether the containment holds under the given set of constraints. So we have seen before this problem, but without any set of constraints. We have seen the constraint-free version of this. Now we just, we introduce a problem where constraints are in place. Okay, and let's see how, I'll try to be quick here, right? Because I think we are almost done. So the strategy is not that different from implication. Essentially, the goal here is to find a version of the query homomorphism theorem, which does this, right? We want to characterize containment under sigma via the existence of a query homomorphism from Q prime, but now not to Q, but to the conjunctive queries that comply with the set of functional dependency sigma, right? So this is the refined version of the query homomorphism theory. So we need to check for a query homomorphism from Q prime, not to Q, but to some transformed version of Q according to sigma, which will act as a representative. And now this should ring a bell now, right? How we are going to transform that. You don't have to be very creative for that. Use the chase, right? That's why we introduced that tool. And essentially what we can prove here is this refined version of the query homomorphism theorem, where the containment holds if there is a query homomorphism from Q2 to the query that we obtain by applying the chase Q1 and function and then sigma. Now, what is this query essentially? The body of this query, it's essentially the set of atoms that you built starting from the set of atoms in Q1, and you apply the chase. Now, what will be the output table of this query? Because we have also the output table, don't forget that. The output table is essentially the table that we get after updating it by applying the chase homomorphism. We call the chase homomorphism, which keeps track of how variables are replaced, right? And therefore, the output table of Q1 should be modified analogously. And this is done by just applying the chase homomorphism there. So this is the new query that we have the transform query that acts as a representative of all the other ones that we should consider. Now here I have a note just to avoid confusion, which says that the queries here are constant free. Although conjunctive queries can mention constants, what I present here, I assume constant free queries. Can someone tell us why I need this assumption at this point? Of course, everything can be generalized to queries with constants, but can someone tell us why, for me now here, is important to assume constant free queries? It's related to what we discussed about the chase before. So recall that the chase for functional dependencies that we discussed doesn't treat very, very carefully constants, right? Recall the case where we have to unify constants and we fail and all these complications. And as I said, I decided to put this aside. Okay, I have to put this aside also here, otherwise we are not consistent, right? So that's why I assume here constant free queries in order to be able to use the chase that we discussed before without any confusion. But of course, one can go to queries with constants, no problem. And this allows us to get this result. Why? Because we can build in polynomial time this new query, the transform query, and then it's just checking for the existence of a homomorphism. So you get the NP, please. Say it again. Right. Yeah, but how you check for this query homomorphism? Look, if you have a procedure which is tractable, and the only thing that you need is to transform your query via the chase, and then you are fine, because we know with functional dependencies in polynomial time you can do it. So if you have a procedure which is p time, then the transformation, it will not change that. Great. So here we get an NP upper bound. Why? Because in polynomial time we build this new query, and then we just check for the existence of a query homomorphism, which is a simple guess and check thing. The lower bound, okay, we have already seen that the problem is NP hard even without constraints, right? So by reducing from, I don't know, maybe 3 colorability or 3 SAD or some problem. There are a lot of proofs. So since the problem is NP hard even without constraints, it's clear that it will be NP hard even with constraints. And that's how we get that. Now, what about inclusion dependencies? I think we are almost there. So what about inclusion dependencies? I'll try to be quick. It's the same story again, right? But the only thing that we can do is to characterize unrestricted containment. It's exactly the same story with unrestricted implication, because the chase with inclusion dependencies builds in principle, in general, infinite sets of atoms. So if we try to prove an analogous result as this one for inclusion dependencies, what we will do is to prove this for the unrestricted version of containment. What is this unrestricted version of containment? You can imagine what is that. It's containment where not only finite, but also infinite databases are taken into account. So Q1 is contained in Q2 under sigma without any restriction, which I denote in this way, if this containment holds for every possibly infinite database, right? Not only finite databases, but. And now we can prove that. It's exactly the same result as for functional dependencies. The difference now here is we can only talk about the unrestricted version of containment. And the reason is because the chase may be infinite, and the only thing that we can prove is that. Now, what do you expect? You expect finite controllability of CQ containment under inclusion dependencies. This is a very interesting result. It's even more difficult to get it compared to implication. It's a deep result. I won't even try to explain how one can get that. But this is a very interesting result, which tells us that plain containment, so restricted, let's say, containment under finite databases, and the unrestricted version are equivalent, right? And putting these things together, we get a characterization of containment via the existence of a query homomorphism from Q2 to this transformed query via the chase. Now, one may say, okay, good, which means that we can build the chase again and check for the query homomorphism, but don't forget, the chase might be infinite. So even here, we need a bit more refined procedure than just building it, because we cannot explicitly build this guy, right? And here, it's again a non-deterministic procedure in the spirit of what we discussed for implication, but things are a bit more complicated now here because it's not that we start from a single atom and we build this chain of atoms, as we discussed before. Now we start from the body of a query, which is a set of atoms, right? So imagine that we are going to do something similar, but not starting from a single atom and non-deterministically build these atoms one after the other without having to remember all the history, but only 2 consecutive atoms. Imagine that we are going to do something similar starting from a set of atoms, which is the body. Things become a bit more complicated there, but it can be done. So non-deterministically, we can construct essentially a subquery, Q prime, of this transform query with at most Q2 atoms. This notation refers to the number of atoms in the body of Q2. So we don't really need more than Q2 atoms in order to check whether Q2 is mapped to the transform query. And this can be done without storing more than 2 times this number of atoms. Similar in spirit with what we did for implication, but now for this number of atoms. I know that this is very, very sketchy and hand-waving, but I fear I can't do better than that at this point, right? But the message is that we cannot afford to build the chase explicitly, but one can build non-deterministically portion of it, which does the job. And once we build that non-deterministically, then it's the same story. We can guess a function and then verify that it's a query homomorphism. And of course, now the whole thing works in polynomial space because the non-deterministic algorithm that we discussed requires p-space. And this is the best that we can do, right? So one can provide a p-space lower bound, which means that this is the best that we can hope for. Now, this p-space lower bound can be a reduction from implication, can be, one can simulate a p-space Turing machine. There are several ways to get it. All right, so this is what I wanted to share with you guys. I hope it's clear what is going on, or at least the high-level picture and the main tools that one should use here. So satisfaction implication, we have seen that before. I don't have to repeat it. For containment, okay, it's again checking for query homomorphism from Q2 to this transform query. And the same story. For functional dependencies, we can explicitly construct the chase. For the inclusion dependencies, we cannot afford that, but we need to non-deterministically build this portion. And again, we heavily rely on the finite controllability of CQ containment. So again, without this result in place, which is a relatively recent result, actually, it's, now I don't remember exactly, but it's not from the 80s. So Diego, when Ricardo proved that, the finite controllability of, I don't remember, 2006, 7, I don't remember. So it's a relatively recent result. It doesn't go back to the 80s. So before 2006, we couldn't use this finite controllability. So we will need something else to prove this result. Okay. So, and I would like to finish with this concluding remark, because as you can see, the chase procedure is a very important tool when it comes to reasoning with constraints, right? And this is one of the main messages that I was trying to convey here. And actually, the chase procedure has been defined not only for inclusion and functional dependencies, but for way more general classes like EGDs, like equality generating dependencies, tuple generating dependencies, and other classes. I mean, whenever we have a rule-based formalism in our hands, right, the obvious thing that people will do is to define the right version of the chase for it. And it has been used actually in several applications. So data exchange has used a lot the chase procedure, computing certain answers in data integration. Ontology mediated query answering heavily relies on that, and I think there will be a lecture in a few days. Data cleaning use that. I think Floris will mention it in his lecture, and the list goes on. So one thing that you should keep from this course is this notion of the chase and what the chase helps us to do, which is in the end is a very intuitive and simple tool to understand. And I think that's it. So thank you very much.